When you think of Pluto, what comes to mind? A tiny frozen rock drifting at the edge of our solar system. A sad little world that got kicked out of the Planetary Club back in 2006. Well, prepare to have everything you thought you knew about this distant world completely turned upside down, because Pluto is hiding secrets that would make even the most seasoned astronomers question everything they believed about planetary science. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Picture this. It's July 14th, 2015, and NASA's New Horizons spacecraft is hurtling toward a world that we've never seen up close. For over 8 decades, Pluto existed in our collective imagination as nothing more than a fuzzy dot of light in our most powerful telescopes. Scientists expected to find a cold, dead, crater-covered ball of ice and rock. Something boring, something simple, something that would confirm our assumptions about how small, distant worlds should behave. But what New Horizons discovered in those first breathtaking images sent back to Earth wasn't just surprising, it was revolutionary. It was paradigm shifting, and it revealed that we had been fundamentally wrong about almost everything we thought we knew about the dwarf planet at the edge of our cosmic neighborhood. Because here's what nobody tells you about Pluto. This world that we dismissed, this object that we demoted, this distant speck that we assumed was geologically dead, is actually one of the most geologically active and dynamically complex worlds in our entire solar system. We're talking about massive ice volcanoes that dwarf anything found on Earth, flowing nitrogen glaciers that reshape the landscape in real time, towering mountain ranges made of water ice harder than steel, and an atmosphere so complex and unusual that it operates unlike any other atmospheric system we've ever encountered. But before we dive into these mind-bending discoveries that are rewriting textbooks and forcing scientists to completely reconsider how planetary bodies work, we need to address the elephant in the room. The controversy that still makes headlines today. The decision that sparked more public outrage than perhaps any other scientific reclassification in modern history. On August 24, 2006, in a conference room in Prague, 424 astronomers made a decision that would forever change how we think about our solar system. With a single vote, they stripped Pluto of its planetary status, relegating it to the newly created category of dwarf planet. But here's what makes this decision so controversial, and why many scientists are still fighting it today. That vote represented less than 5% of the world's professional astronomers. Most of the international delegates had already gone home, and the criteria they used to define a planet created such arbitrary distinctions that it would actually disqualify Earth as a planet if our world were located in Pluto's distant orbit. The man leading NASA's New Horizons mission to Pluto, Alan Stern, didn't mince words about his feelings on this reclassification. He called it embarrassing for astronomy. And as we'll see throughout this journey, the data we've collected since 2006 suggests he might have been right to be upset. Because every single discovery we've made about Pluto has revealed it to be more planet-like, not less. But let's step back for a moment and talk about how this distant world first captured our attention. The story begins in 1930 with a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. Tombor was tasked with a seemingly impossible job: find a hypothetical ninth planet that mathematician Percival Lowell had predicted must exist based on tiny perturbations in the orbits of Uranus and Neptune. For months, Tombor methodically photographed the same regions of sky, then used a device called a blink comparator to look for objects that had moved between exposures. It was tedious work, like looking for a needle in a cosmic haystack. But on February 18th, 1930, Tombor spotted something extraordinary: a faint point of light that had shifted position between two photographic plates taken 6 days apart. That tiny moving dot was Pluto, and its discovery made headlines around the world. Here was the ninth planet, the final member of our solar system family, located exactly where mathematical predictions suggested it should be. The name Pluto was suggested by an 11-year-old girl named Venetia Burney, after the Roman god of the underworld, and it seemed perfect for this distant, dark world at the edge of known space. For 76 years, Pluto held its place in our solar system's planetary lineup. Generations of school children memorized the phrase, "My very educated mother just served us 9 pizzas," to remember the order of the planets. Pluto appeared on everything from textbooks to lunchboxes, cementing its place in popular culture as our solar system's smallest and most mysterious world. But even from the beginning, Pluto was different. Its orbit was highly eccentric and tilted compared to the other planets. It was much smaller than expected. And as our observational capabilities improved, it became clear that Pluto shared its orbital neighborhood with thousands of other icy objects in a region we now call the Kuiper Belt. The discovery of these other Kuiper Belt objects, particularly one called Eris in 2005 that was actually more massive than Pluto, forced astronomers to confront a difficult question. If Pluto was a planet, then shouldn't these other objects be planets too? Were we prepared to accept a solar system with dozens or even hundreds of planets? The International Astronomical Union decided the answer was no. They established 3 criteria for planetary status. A planet must orbit the Sun, must have enough mass to assume a roughly spherical shape, and must have cleared its orbital neighborhood of other objects. Pluto met the first 2 criteria but failed the third, sharing its orbital space with countless other Kuiper Belt objects. And so, with that controversial vote in Prague, our solar system officially went from 9 planets to 8, and Pluto found itself reclassified as a dwarf planet, grouped with other similar objects like Ceres, Eris, Makemake, and Haumea. But here's where the story gets really interesting, because just 9 years after that reclassification, New Horizons began beaming back images and data that revealed Pluto to be far more extraordinary than anyone had dared to imagine. And every single discovery made the 2006 decision look more questionable. The first hint that we were in for surprises came from the earliest images, when New Horizons was still millions of miles away from its target. Instead of the uniform cratered surface that scientists expected, the images revealed distinct regions with dramatically different colors and textures. There were bright areas and dark areas, smooth plains and rugged terrain, all on a world that was supposed to be geologically dead. But nothing could have prepared the scientific community for what they saw when New Horizons made its closest approach on July 14th, 2015. The images that came back didn't just show a complex world, they showed a world that was actively reshaping itself through geological processes that shouldn't have been possible on such a small, distant object. The most iconic feature visible in those first high-resolution images was a massive, heart-shaped region that scientists named Tombor Regio in honor of Pluto's discoverer. This wasn't just a pretty pattern on the surface. It was a geological feature spanning over 1,000 miles across, containing some of the youngest terrain found anywhere in the outer solar system. The western lobe of this heart-shaped region, called Sputnik Planitia, turned out to be a vast plain of nitrogen ice, smooth and crater-free, indicating that it was geologically very young. But this wasn't static ice. The nitrogen was actually flowing like a glacier, churning and convecting in massive cells that were constantly refreshing the surface. At temperatures of -380 degrees Fahrenheit, where water ice becomes as hard as granite, nitrogen ice was flowing and reshaping the landscape in real time. Surrounding this nitrogen ice plain were towering mountain ranges made of water ice, some peaks reaching heights of over 2 miles above the surrounding terrain. These weren't impact crater rims or simple geological features. They were complex mountain systems that required active geological processes to form and maintain. But perhaps the most shocking discovery of all was the identification of what appeared to be massive cryovolcanoes, or ice volcanoes, scattered across Pluto's surface. These weren't small features. We're talking about volcanic structures that dwarf similar features found anywhere else in the solar system. The largest of these cryovolcanoes, Wright Mons and Picard Mons, tower several kilometers above Pluto's surface and span hundreds of kilometers in diameter. Wright Mons alone is roughly the size of Mauna Loa in Hawaii, one of Earth's largest volcanoes. But instead of erupting molten rock, these alien volcanoes expelled a mixture of water, ice, ammonia, and other volatiles that would have had the consistency of thick slush due to Pluto's extreme cold. The implications of these discoveries were staggering. Here was a world only 1/6 the mass of our moon, located nearly 40 times farther from the sun than Earth, somehow maintaining enough internal heat to drive large-scale geological processes. This wasn't supposed to be possible according to our understanding of planetary thermal evolution. Small worlds like Pluto should have lost their internal heat billions of years ago, becoming geologically inactive shortly after their formation. The fact that we were seeing evidence of recent geological activity, possibly within the last few million years, meant that our models for how small planetary bodies evolve over time needed to be completely revised. And the surprises didn't stop there. Pluto's atmosphere, which was expected to be thin and simple, turned out to be far more complex and extensive than anyone had predicted. New Horizons detected atmospheric haze layers extending over 50 miles above Pluto's surface, created by complex chemical processes involving methane, nitrogen, and other compounds. These atmospheric processes were creating organic compounds called tholins, which were responsible for Pluto's distinctive reddish-brown coloration in many regions. But more importantly, the atmosphere was actively losing material to space, with some of that escape material being captured by Pluto's largest moon, Charon, creating distinctive reddish polar regions on that world as well. As the complexity of Pluto's atmospheric system became even more apparent when the James Webb Space Telescope, nearly a decade after New Horizons' flyby, confirmed that atmospheric haze wasn't just a visual curiosity. the haze was actually controlling Pluto's entire climate system, simultaneously cooling the atmosphere while providing energy for molecular species to escape into space. This made Pluto's atmospheric dynamics unlike anything else known in our solar system. Each new discovery about Pluto has painted a picture of a world that defies our expectations and challenges our understanding of how planetary bodies should behave. This isn't the cold, dead rock that we imagined for over 8 decades. This is a geologically active, atmospherically complex, dynamically evolving world that continues to surprise scientists with each new analysis of New Horizons data. But we're just getting started on this journey of discovery, because the story of Pluto's unexpected complexity goes far beyond active geology and unusual atmospheric chemistry. Recent evidence suggests that this distant world may harbor secrets that could fundamentally change how we think about the potential for life in the outer solar system. The evidence for these extraordinary claims lies hidden beneath Pluto's frozen surface, in a realm that no spacecraft has directly observed, but that scientists are now convinced must exist. We're talking about a subsurface ocean of liquid water, maintained by processes that shouldn't be possible on a world so far from the sun's warming influence. The clues began emerging when scientists analyzed the distribution of Pluto's geological features and realized that the patterns they were seeing could only be explained by the presence of liquid water beneath the surface. The massive cryovolcanoes we discussed weren't just erupting random mixtures of ice. They were tapping into reservoirs of liquid water that had been kept from freezing by the presence of natural antifreeze compounds like ammonia. Think about what this means. Here's a world that receives only 1/1600th the amount of sunlight that Earth does, where surface temperatures never rise above -350 degrees Fahrenheit, somehow maintaining liquid water in its interior. The implications are staggering, because wherever we find liquid water, organic compounds, and energy sources on Earth, we find life. But the story gets even more remarkable when we consider the recent discovery of what scientists believe may be a supervolcano on Pluto's surface. In 2024, researchers studying New Horizons data identified a peculiar crater-like feature called Kyladze, located near the heart-shaped Tombor Regio. At first glance, Kyladze looked like it might be an impact crater formed by a meteorite collision. But closer analysis revealed characteristics that set it apart from typical impact features. The crater is slightly elongated rather than perfectly circular, and it lacks the central peak that would normally be expected from a meteorite impact of that size. Instead, its characteristics match those of a volcanic caldera, a large depression formed when a volcano collapses after expelling massive amounts of material from beneath the surface. The scale of this potential supervolcano is breathtaking. Scientists estimate that Kyladze could have expelled more than 1,000 cubic kilometers of icy material in a single eruption event. To put that in perspective, that's enough material to bury the entire state of Rhode Island under a layer of ice nearly 2 miles thick. And based on the lack of impact craters in the surrounding area, this eruption likely occurred within the last few million years, making it geologically recent by planetary standards. The discovery of potential supervolcanic activity on Pluto adds yet another layer to the complex geological story of this distant world. But it also raises profound questions about the heat sources that could drive such massive eruptions. Traditional models suggest that a world of Pluto's size should have exhausted its internal heat sources billions of years ago. Yet the evidence clearly shows ongoing geological activity that requires significant energy input. One possibility is that Pluto's interior contains more radioactive elements than previously calculated, providing a long-term heat source through radioactive decay. Another potential explanation involves tidal heating from gravitational interactions with Pluto's moon Charon. Although Pluto and Charon are tidally locked, meaning they always show the same face to each other, their elliptical orbits could still generate enough tidal flexing to produce heat through friction. But perhaps the most intriguing possibility is that Pluto's geological activity is connected to its subsurface ocean in ways that create a self-sustaining system. As liquid water moves through the interior, it could carry heat from the core to the surface, driving cryovolcanic eruptions that then expose fresh water ice to the surface environment. This water ice could then be recycled back into the interior through various geological processes, creating a dynamic system that maintains activity over geological timescales. The evidence for this complex interior dynamic extends beyond the volcanic features themselves. Scientists have identified networks of ridges and valleys on Pluto's surface that appear to be created by tectonic processes, similar to the rift valleys found on Earth where continental plates are pulling apart. These features suggest that Pluto's interior is not only geologically active, but may be undergoing large-scale structural changes that reshape the surface over time. The presence of these tectonic features, combined with the cryovolcanic activity and the flowing nitrogen ice plains, paints a picture of a world that is far more geologically dynamic than any other small planetary body we've studied. Even Mars, which is significantly larger than Pluto and much closer to the Sun, shows less evidence of recent geological activity. This level of geological complexity becomes even more remarkable when we consider Pluto's location in the Kuiper belt, a region of space that was once thought to be populated by primitive, unchanged remnants from the early solar system. The traditional view held that objects in this distant region would have remained largely unaltered since their formation 4.5 billion years ago, preserving a record of conditions in the early solar nebula. But Pluto's geological activity demonstrates that even in the cold, distant reaches of the outer solar system, planetary evolution continues. This discovery has forced scientists to reconsider their assumptions about the entire Kuiper belt and has sparked new interest in exploring other large objects in this region. The implications extend far beyond Pluto itself. If a world of Pluto's size can maintain geological activity and potentially subsurface liquid water, what about the hundreds of other large Kuiper belt objects that we haven't yet explored? Could worlds like Eris, Makemake, or Haumea also harbor complex geological processes and possibly even conditions suitable for life? Recent discoveries have already begun to hint at the diversity that exists among these distant worlds. The dwarf planet Haumea, for example, has an unusual elongated shape and rapid rotation that suggest it experienced a massive collision in its past. Makemake appears to have a thin atmosphere and possibly active surface processes. And Eris, which is actually more massive than Pluto, likely has its own complex geological and atmospheric systems waiting to be explored. The discovery in 2024 of a new large Kuiper belt object, called 2017 OF201, potentially the second largest known object in such a distant orbit, suggests that we've only scratched the surface of what exists in the outer solar system. This object, which may be large enough to qualify as a dwarf planet, orbits at distances so extreme that it takes over 1,000 years to complete a single trip around the Sun. The existence of such distant objects raises fascinating questions about the formation and evolution of our solar system. How did these objects end up in such remote orbits? What processes shaped their development over billions of years? And most intriguingly, how many more similar objects are waiting to be discovered in the dark reaches beyond Neptune? Scientists estimate that there could be hundreds of objects similar to Pluto scattered throughout the Kuiper belt and beyond, each potentially harboring its own unique geological and atmospheric characteristics. The region that was once considered empty space between the planets is now known to be populated with a diverse family of worlds, each with its own story to tell about the history and evolution of our solar system. This growing understanding of Kuiper belt diversity has profound implications for how we define and categorize planetary bodies. The arbitrary distinction between planets and dwarf planets becomes increasingly meaningless when we consider that some dwarf planets display more geological complexity than several of the traditional planets. Mercury, for example, is geologically dead and has been for billions of years. Mars shows some evidence of past geological activity, but appears to be largely inactive today. Yet Pluto, classified as a mere dwarf planet, displays ongoing geological processes that rival those found on Earth. The classification system established in 2006 fails to capture these fundamental differences in planetary behavior and evolution. As we continue to analyze the wealth of data returned by New Horizons and make new observations with advanced telescopes like James Webb, our understanding of Pluto continues to evolve. Each new discovery reveals additional layers of complexity that challenge our preconceptions about how planetary bodies should behave. The story of Pluto has become a powerful reminder that the universe is far stranger and more wonderful than our theories predict. This distant world, once dismissed as an insignificant ice ball, has emerged as one of the most fascinating and geologically active bodies in our solar system. And as we'll see, the surprises are far from over. The relationship between Pluto and its largest moon Charon represents one of the most unusual planetary system dynamics found anywhere in our solar system. And it's a story that reveals just how much we still don't understand about gravitational relationships in space. When Charon was first discovered in 1978, it immediately changed everything we thought we knew about Pluto's basic properties. Suddenly, astronomers could calculate Pluto's actual mass for the first time, and the results were shocking. Pluto was much smaller and less massive than anyone had predicted. But Charon's discovery revealed something even more extraordinary. This wasn't just a typical moon orbiting a planet. Charon is roughly half the size of Pluto itself, making it the largest moon relative to its parent planet anywhere in our solar system. The gravitational relationship between these two bodies is so unusual that they don't really behave like a planet and moon at all. Instead, they orbit around a common point in space that lies between them, like a cosmic dance performed by two partners of nearly equal size. Scientists now refer to Pluto and Charon as a binary system or double planet. And this unique orbital arrangement has profound implications for both worlds. The two bodies are tidally locked, meaning they always show the same face to each other as they orbit their common center of mass every 6 days. This creates a situation where, if you were standing on Pluto's surface, Charon would appear to hang motionless in the sky, never rising or setting, always occupying the same position above the horizon. But the relationship between these two worlds goes far beyond simple gravitational attraction. Recent observations with the James Webb Space Telescope have revealed that material from Pluto's atmosphere is continuously being captured by Charon, creating distinctive surface features that tell the story of ongoing atmospheric transfer between planetary bodies. The reddish polar regions visible on Charon's surface are thought to result from methane molecules escaping from Pluto's atmosphere, traveling across the space between the two worlds, and then undergoing chemical transformations when they freeze onto Charon's surface. This atmospheric transfer represents a process unlike anything observed elsewhere in our solar system. We're watching real-time evolution of two planetary bodies that are actively influencing each other's surface composition and atmospheric chemistry. The organic compounds created through this process, called tholins, are the same materials that give Pluto its distinctive reddish-brown coloration in many regions. But on Charon, these compounds are being deposited in specific patterns that reveal the complex dynamics of how atmospheric escape and capture work in low-gravity environments. The James Webb Telescope has also detected carbon dioxide and hydrogen peroxide on Charon's frozen surface, providing new insights into the chemical processes occurring throughout this distant system. These discoveries suggest that Charon is not simply a passive recipient of material from Pluto's atmosphere, but may have its own active surface chemistry that transforms the compounds it receives into new molecular species. The detection of these specific chemicals has important implications for understanding how icy bodies throughout the outer solar system may have formed and evolved. Carbon dioxide and hydrogen peroxide can only exist on Charon's surface under very specific temperature and radiation conditions, and their presence provides clues about the history of chemical processes that have shaped both Pluto and Charon over billions of years. But perhaps the most remarkable aspect of the Pluto-Charon system is what it tells us about the potential for complex geological interactions between closely paired planetary bodies. The gravitational forces between Pluto and Charon may be responsible for some of the geological activity we observe on Pluto's surface. Although the two bodies are tidally locked in their current configuration, their orbital relationship may not have always been so stable. Early in their history, when Pluto and Charon were likely much closer together, the tidal forces between them would have been far stronger. These forces could have generated significant internal heating through tidal flexing, similar to the processes that keep Jupiter's moon Io volcanically active today. Even now, subtle variations in their elliptical orbits may continue to generate enough tidal heating to contribute to Pluto's ongoing geological activity. The formation of the Pluto-Charon system itself remains one of the great mysteries of planetary science. The most widely accepted theory suggests that both worlds formed from a massive collision between two large Kuiper belt objects billions of years ago. This impact would have been so energetic that it vaporized and scattered material throughout the region, which then recondensed and coalesced to form the current system. This collision theory helps explain several puzzling characteristics of both Pluto and Charon, including their unusual density differences and the fact that Charon appears to have a much smaller proportion of volatile materials compared to Pluto. If both worlds formed from the debris of a single massive impact, the lighter, more volatile materials might have preferentially accumulated on the larger body, which became Pluto, while the denser, rockier materials formed Charon. But the Pluto-Charon system includes even more complexity than just these two main bodies. 4 smaller moons, Nix, Hydra, Styx, and Kerberos, orbit the system in a complex gravitational dance that continues to puzzle astronomers. These tiny moons likely formed from the same impact event that created Pluto and Charon, but their orbital characteristics suggest a more complicated formation history than simple debris accumulation. The small moons orbit in a series of resonances with each other and with the Pluto-Charon binary, creating a dynamically stable but intricate system that has persisted for billions of years. Some of these moons appear to wobble chaotically as they orbit, tumbling end over end in unpredictable patterns due to the complex gravitational influences of multiple bodies pulling on them simultaneously. This multi-body orbital system provides a natural laboratory for studying gravitational dynamics that simply doesn't exist anywhere else in our solar system. The interactions between Pluto, Charon, and the 4 smaller moons create gravitational resonances and tidal effects that may influence geological processes on all the bodies involved. Recent computer simulations have suggested that the gravitational interactions within this complex system may have played a crucial role in shaping Pluto's current geological features. The location of major surface features like Sputnik Planitia may not be random, but could instead reflect the gravitational influence of Charon and the smaller moons over geological timescales. These gravitational effects become even more interesting when we consider that Sputnik Planitia, the smooth nitrogen ice plain within Pluto's heart-shaped region, appears to be located almost exactly opposite to Charon's position in Pluto's sky. This antipodal relationship could be more than coincidence. The massive nitrogen ice deposit may represent a gravitational response to tidal forces from Charon, creating a preferential location for volatile materials to accumulate over billions of years. If this interpretation is correct, then Charon isn't just passively orbiting Pluto, it's actively shaping Pluto's surface geology through long-term gravitational influences that redistribute material across the dwarf planet's surface. This would make the Pluto-Charon system an example of active geological coupling between 2 planetary bodies, a process that could be occurring in binary systems throughout the universe. The implications of such geological coupling extend far beyond our solar system. As we discover more and more binary planetary systems around other stars, understanding how gravitational interactions can drive geological processes becomes crucial for predicting the evolution and habitability of these distant worlds. But the story of Pluto's complexity doesn't end with its unusual moon system. Recent discoveries have revealed that Pluto may be part of a much larger population of similar worlds scattered throughout the outer solar system, and these discoveries are forcing astronomers to completely reconsider what we thought we knew about the architecture of planetary systems. The detection of 2017 OF201, a massive object orbiting at distances so extreme that it takes over 1,000 years to complete a single orbit around the Sun, represents just the latest example of how our understanding of the outer solar system continues to evolve. This object, potentially large enough to qualify as a dwarf planet, suggests that the region of space beyond Neptune is far more populated and diverse than we ever imagined. Scientists estimate that this single discovery implies the existence of hundreds of similar objects that are simply too distant and too faint to detect with current technology. We may be looking at a vast population of Pluto-like worlds, each potentially harboring its own complex geological processes, atmospheric systems, and moon systems. The existence of such a large population of distant worlds has profound implications for our understanding of solar system formation. These objects represent some of the most primitive materials in our solar system, largely unchanged since the earliest days of planetary formation 4.5 billion years ago. But as we've seen with Pluto, even these ancient worlds can maintain active geological processes that continue to shape their surfaces today. The diversity among known dwarf planets already hints at the variety we might find in this larger population. Haumea spins so rapidly that it's stretched into an elongated shape, suggesting it experienced a massive collision that shattered it into fragments. Some of these fragments still orbit Haumea as moons, creating a collision family that preserves evidence of ancient impact events. Makemake appears to have a thin atmosphere and shows spectroscopic evidence of surface processes that may involve seasonal changes as it orbits the Sun. Eris, which is actually more massive than Pluto, likely has its own complex geological and atmospheric systems that could rival or exceed the complexity we've discovered on Pluto. But perhaps the most intriguing aspect of this growing population of distant worlds is what it suggests about the potential for life in the outer solar system. If Pluto can maintain subsurface liquid water and active geological processes at distances of nearly 40 astronomical units from the Sun, what about objects that are even larger or have different compositions? The discovery that geological activity can persist in such cold, distant environments fundamentally changes how we think about habitable zones around stars. The traditional concept of a habitable zone focused on the narrow range of distances where liquid water could exist on a planetary surface. But Pluto demonstrates that subsurface oceans can exist far beyond these traditional boundaries, potentially extending the habitable zone to include the entire outer solar system. This expanded view of habitability has enormous implications for the search for life beyond Earth. If subsurface oceans can exist on worlds as small and distant as Pluto, then the number of potentially habitable environments in our galaxy could be orders of magnitude larger than previously calculated. Every star system with a population of icy bodies in its outer regions could potentially harbor multiple worlds with subsurface oceans and the complex chemistry necessary for life. The chemical processes occurring on Pluto and Charon, involving organic compound formation and atmospheric transfer between worlds, provide examples of the types of complex chemistry that could occur throughout such systems. The tholins being created through these processes are similar to organic compounds that may have played important roles in the origin of life on Earth, suggesting that the ingredients for life may be common throughout the outer regions of planetary systems. As we continue to study Pluto and plan future missions to explore other worlds in the outer solar system, we're likely to discover that the complexity and diversity we've found at Pluto is just the beginning. Each new world we explore will probably reveal its own unique combination of geological processes, atmospheric chemistry, and evolutionary history. The story of Pluto has become a powerful reminder that our universe is far more complex and interesting than our theories predict. This world that we once dismissed as an insignificant ice ball has emerged as a geologically active, atmospherically complex, and potentially habitable environment that challenges every assumption we had about planetary evolution in the outer solar system. And as we're about to discover, the surprises hidden within this distant world are far from over. Because recent evidence suggests that Pluto may be harboring secrets that could revolutionize our understanding of not just planetary science, but the very conditions that make life possible throughout the universe. The secrets hidden beneath Pluto's frozen surface are becoming increasingly difficult to ignore, and they're painting a picture of a world that operates according to rules we're only just beginning to understand. When scientists first began analyzing the chemical composition of those massive cryovolcanic eruptions, they discovered something that shouldn't have been possible. Mixed within the water ice were significant concentrations of ammonia, acting as a natural antifreeze that could maintain liquid conditions at temperatures where pure water would freeze solid. Think about what this means for a moment. We're not just talking about isolated pockets of liquid water that might exist temporarily during volcanic eruptions. We're talking about stable, long-term reservoirs of liquid water that could persist for millions or even billions of years beneath Pluto's surface. The ammonia doesn't just lower the freezing point of water. It creates an environment where complex chemical reactions could occur over geological timescales. But the implications go far deeper than simple chemistry. The presence of these ammonia-water mixtures suggests that Pluto's subsurface ocean isn't just a static body of liquid trapped beneath the ice. It's a dynamic, chemically active system that could support the types of complex organic chemistry that we associate with the emergence of life. And recent computer models suggest that this ocean could be far larger than anyone initially suspected. Scientists now estimate that Pluto's subsurface ocean could contain more liquid water than all of Earth's oceans combined. This isn't speculation based on wishful thinking. It's a conclusion drawn from careful analysis of Pluto's gravitational field, the distribution of surface features, and the energy requirements needed to drive the geological activity we observe. The numbers are staggering. We're potentially looking at a body of liquid water with a volume exceeding 1.3 billion cubic kilometers, hidden beneath an icy shell that may be only tens of kilometers thick. The existence of such a massive subsurface ocean would make Pluto one of the most water-rich worlds in our solar system, rivaling or exceeding the liquid water content of Jupiter's moon Europa or Saturn's moon Enceladus. But unlike those moons, which maintain their subsurface oceans through tidal heating from their massive parent planets, Pluto's ocean would be sustained by internal processes that we don't yet fully understand. One possibility involves the slow decay of radioactive elements in Pluto's rocky core. Unlike the earlier estimates that suggested Pluto should have exhausted its radioactive heat sources billions of years ago, newer models incorporating updated knowledge of Kuiper belt object formation suggest that Pluto could contain significantly more long-lived radioactive isotopes than previously calculated. Elements like uranium, thorium, and potassium could continue providing heat for billions of years, slowly warming the interior and maintaining liquid water in the subsurface ocean. But radioactive decay alone might not be sufficient to explain the level of geological activity we observe on Pluto's surface. Another potential heat source involves the complex gravitational interactions within the Pluto-Charon system. While the two bodies are currently tidally locked, their orbital relationship has likely evolved significantly over the billions of years since their formation. During earlier periods when their orbits were less stable, the tidal forces between them could have generated substantial internal heating through gravitational flexing. Even now, subtle variations in their elliptical orbits continue to create tidal bulges that flex Pluto's interior. These tidal forces may seem insignificant compared to the dramatic tidal heating we see on Jupiter's volcanic moon, Io, but over geological timescales, even small amounts of tidal heating could contribute to maintaining Pluto's internal warmth and driving the geological processes we observe. Recent analysis of Pluto's surface features has revealed additional evidence supporting the existence of a large subsurface ocean. The distribution of geological features across Pluto's surface shows patterns that can only be explained by large-scale convection currents within the interior. These patterns suggest that heat from the deep interior is being transported to the surface through a complex system of convection cells, similar to the processes that drive plate tectonics on Earth. The smooth young surfaces we see in regions like Sputnik Planitia may represent locations where this internal convection brings warm material close to the surface, creating conditions that allow for active resurfacing through cryovolcanic processes. The lack of impact craters in these regions indicates that the surface is being continuously renewed through geological activity, requiring ongoing heat sources and active material transport from the interior. But perhaps the most compelling evidence for Pluto's subsurface ocean comes from the detection of specific chemical compounds on the surface that could only have formed through water-rock interactions in a liquid environment. Spectroscopic analysis of Pluto's surface has identified complex organic molecules that require liquid water and significant time to form. These compounds, including various hydrocarbons and nitrogen-bearing organic molecules, suggest that chemical evolution has been occurring within Pluto's subsurface ocean for extended periods. The presence of these organic compounds is particularly significant because they represent some of the same types of molecules that scientists believe were crucial for the emergence of life on early Earth. The detection of these compounds on Pluto's surface indicates that they're being transported from the subsurface ocean to the surface through cryovolcanic processes, providing a direct window into the chemistry occurring in Pluto's hidden ocean. This chemical evidence becomes even more intriguing when we consider the energy sources that could drive complex chemistry within Pluto's subsurface environment. The interaction between liquid water and Pluto's rocky core could create conditions similar to the hydrothermal vents found on Earth's ocean floors, where some scientists believe life may have first emerged. These hydrothermal systems could provide both the chemical building blocks and the energy sources necessary to support complex organic chemistry. The rocky material in Pluto's core likely contains a variety of minerals that could participate in water rock reactions, creating chemical gradients and energy sources that could sustain complex chemistry over geological timescales. The presence of sulfur-bearing compounds detected on Pluto's surface suggests that sulfur chemistry, which plays important roles in many Earth-based life forms, could also be occurring within Pluto's subsurface environment. Recent discoveries have also revealed that Pluto's subsurface ocean may not be isolated from the surface environment. The cryovolcanic eruptions we've discussed represent direct connections between the subsurface ocean and the surface, allowing for the exchange of materials and possibly even providing pathways for any subsurface life forms to reach the surface environment. This connectivity between subsurface and surface environments creates possibilities for complex ecosystem interactions that could sustain life in multiple environmental niches. The atmospheric escape processes occurring on Pluto add another layer of complexity to this picture. As material from Pluto's atmosphere escapes into space, some of it is captured by Charon, while other escaped material may eventually fall back to Pluto's surface in different locations. This atmospheric circulation could create a planet-wide system for distributing organic compounds and other materials between different surface regions, and potentially even between the surface and subsurface environments. The implications of these discoveries extend far beyond Pluto itself. If a world as small and distant as Pluto can maintain a large subsurface ocean with active chemistry, then the potential for similar environments throughout the outer solar system becomes enormous. The hundreds of large Kuiper belt objects that remain unexplored could each represent unique laboratories for the types of chemistry that might support life. But the story becomes even more remarkable when we consider recent evidence suggesting that Pluto's geological activity may be increasing rather than decreasing over time. Analysis of the crater densities on different regions of Pluto's surface indicates that some of the most recent geological activity has occurred within the last few million years, and possibly even more recently than that. The Kiladze supervolcano that we discussed earlier shows evidence of multiple eruption events, with the most recent potentially occurring within the last million years. This represents an incredibly short time period in geological terms, suggesting that whatever processes are driving Pluto's geological activity are not only ongoing, but may be accelerating. This acceleration of geological activity could be related to changes in Pluto's orbital position as it follows its highly elliptical path around the Sun. Pluto's distance from the Sun varies significantly over its 248-year orbital period, and these changes in solar heating could trigger variations in atmospheric pressure that influence subsurface processes. As Pluto approaches its closest point to the Sun, increased solar heating could create atmospheric pressure changes that affect the stability of subsurface volatile reservoirs, potentially triggering increased volcanic activity. The timing of New Horizons' flyby in 2015 may have been particularly fortuitous, as Pluto was relatively close to its perihelion, or closest approach to the Sun, which occurred in 1989. This timing could explain why the spacecraft observed such active geological processes and extensive atmospheric haze layers. If this interpretation is correct, then Pluto's geological activity may follow cyclical patterns related to its orbital motion, with periods of increased activity alternating with more quiescent phases. But even during its most distant orbital phases, Pluto appears to maintain enough geological activity to continuously reshape its surface. The presence of the smooth nitrogen ice plains in Sputnik Planifia, which show no evidence of impact cratering, indicates that surface renewal processes operate continuously, regardless of Pluto's orbital position. This suggests that the primary drivers of Pluto's geological activity are internal rather than external, related to the subsurface ocean and internal heat sources rather than solar heat-in variations. The continuous nature of Pluto's geological activity has profound implications for the potential habitability of its subsurface environment. Unlike worlds that may have been habitable only during brief periods in their history, Pluto appears to have maintained conditions suitable for complex chemistry throughout most of its 4.5 billion-year existence. This long-term stability could have provided the time necessary for the emergence and evolution of life. if the right chemical conditions existed within the subsurface ocean. Recent theoretical work has suggested that the chemical environment within Pluto's subsurface ocean could be remarkably Earth-like in some respects. The presence of dissolved minerals from water-rock interactions, combined with organic compounds delivered through cryovolcanic processes, could create a chemical soup rich in the building blocks of life. The energy sources available through hydrothermal activity and radioactive decay could provide the thermodynamic driving forces necessary to sustain complex biochemistry. But perhaps the most intriguing possibility is that Pluto's subsurface ocean could support not just the chemistry of life, but actual living organisms. The detection of complex organic molecules on Pluto's surface, combined with evidence for liquid water and energy sources in the subsurface, creates a compelling case for the potential habitability of this distant world. While we're still far from having direct evidence for life on Pluto, the conditions appear to be more favorable than anyone would have imagined just a decade ago. The search for life on Pluto would require future missions capable of directly sampling the subsurface ocean or analyzing the materials expelled by cryovolcanic eruptions. Such missions remain technologically challenging and would require significant advances in spacecraft design and propulsion systems. But the potential scientific rewards would be enormous, as the discovery of life in Pluto's subsurface ocean would fundamentally change our understanding of the prevalence and diversity of life throughout the universe. The story of Pluto's hidden ocean and potential habitability represents just one chapter in the larger story of this remarkable world. As we continue to analyze the data returned by New Horizons and make new observations with advanced ground-based and space-based telescopes, our understanding of Pluto continues to evolve in directions that none of us could have predicted when the spacecraft was first launched in 2006. Each new discovery about Pluto forces us to reconsider our assumptions about planetary evolution, habitability, and the diversity of worlds that exist throughout the universe. This distant dwarf planet has emerged as one of the most scientifically fascinating objects in our solar system, challenging our understanding of geology, atmospheric science, and astrobiology in ways that continue to surprise and delight researchers around the world. But the surprises hidden within Pluto's complex systems are far from exhausted. Recent advances in our observational capabilities and theoretical understanding are revealing new aspects of this distant world that promise to keep scientists busy for decades to come. And as we're about to discover, some of the most remarkable secrets about Pluto may involve processes and phenomena that stretch the boundaries of what we thought was possible in planetary science. The atmospheric dynamics occurring on Pluto have revealed processes so unique and counterintuitive that they're forcing atmospheric scientists to develop entirely new models for how planetary atmospheres can behave. When New Horizons first transmitted images showing Pluto's atmospheric haze layers extending over 50 miles above the surface, scientists initially assumed these were simple photochemical smogs, similar to what we might find on Saturn's moon Titan. But detailed analysis of the spectroscopic data revealed something far more extraordinary. The haze particles in Pluto's atmosphere aren't just passive byproducts of chemical reactions. They're actively controlling the thermal structure of the entire atmospheric system through a process that scientists are calling radiative convective coupling. This means that the tiny particles suspended in Pluto's thin atmosphere are simultaneously absorbing energy from sunlight, radiating heat back into space, and creating convection currents that drive atmospheric circulation patterns unlike anything observed elsewhere in our solar system. Think about how remarkable this is. On Earth, our thick atmosphere is heated primarily from below by the warm surface, creating the convection patterns that drive our weather systems. On Mars, the thin atmosphere is heated directly by solar radiation, creating simpler circulation patterns. But on Pluto, the atmospheric haze itself becomes the primary heat engine, creating a three-dimensional circulation system powered by microscopic particles floating in near-vacuum conditions. The implications of this atmospheric behavior extend far beyond simple meteorology. The haze-driven circulation patterns are actively transporting material around Pluto's globe, redistributing organic compounds, volatile gases, and even fine dust particles between different surface regions. This atmospheric transport system may be one of the key mechanisms allowing Pluto to maintain its complex surface chemistry over geological timescales. Recent computer simulations have shown that these atmospheric circulation patterns could create seasonal cycles that persist for decades or even centuries, driven not by changes in solar heating as on Earth, but by the slow evolution of haze particle properties as they undergo continuous chemical transformations in Pluto's radiation environment. During some phases of these long-term cycles, the atmospheric circulation could favor the deposition of organic compounds in specific surface regions, while during other phases, these same regions might experience net erosion and material transport to other areas of the planet. This dynamic atmospheric system becomes even more intriguing when we consider its interaction with Pluto's geological processes. The atmospheric pressure variations created by haze-driven circulation could influence the stability of subsurface volatile reservoirs, potentially triggering cryovolcanic eruptions when atmospheric conditions reach certain thresholds. This creates the possibility of feedback loops between atmospheric and geological processes that could maintain Pluto's activity levels over much longer timescales than purely internal heat sources would allow. The chemical complexity of Pluto's atmospheric system has also revealed unexpected connections to the processes occurring in its subsurface ocean. Spectroscopic analysis has identified atmospheric compounds that appear to originate from deep within Pluto's interior, transported to the surface through cryovolcanic processes, and then released into the atmosphere through sublimation of surface ices. This creates a direct chemical link between Pluto's hidden subsurface environment and the atmospheric chemistry visible from space. Among the most surprising atmospheric discoveries has been the detection of complex hydrocarbon molecules that shouldn't be stable under Pluto's radiation conditions. These compounds appear to be continuously replenished through some active process, suggesting that Pluto's surface or subsurface environment contains chemical factories that are constantly producing new organic molecules and releasing them into the atmosphere. The presence of these complex organic molecules in Pluto's atmosphere has profound implications for understanding the chemical evolution of organic compounds in the outer solar system. Some of these molecules are similar to compounds that scientists believe played important roles in the origin of life on Earth, suggesting that the chemical building blocks of life may be common throughout the cold, distant regions of planetary systems. But perhaps the most remarkable aspect of Pluto's atmospheric chemistry is its apparent ability to create increasingly complex molecules over time. Unlike most planetary atmospheres, where chemical evolution tends towards simpler, more stable compounds, Pluto's atmosphere appears to be a site of ongoing chemical complexification, where simple starting materials are continuously transformed into larger, more intricate molecular structures. This chemical evolution process is driven by a combination of solar ultraviolet radiation, cosmic ray interactions, and the unique three-dimensional circulation patterns created by atmospheric haze particles. The result is an atmospheric laboratory where organic chemistry experiments have been running continuously for millions of years, creating a natural archive of chemical evolution that may preserve clues about the types of processes that could lead to the emergence of life. The atmospheric escape processes occurring on Pluto add yet another layer of complexity to this already intricate system. As we mentioned earlier, Pluto is continuously losing atmospheric material to space at a rate of about 1.3 kilograms per second. But this isn't a simple, uniform process. Different atmospheric compounds escape at different rates, and the spatial distribution of atmospheric loss varies across Pluto's surface in ways that reflect the complex interaction between atmospheric circulation, surface composition, and magnetic field effects. Some of the escaped atmospheric material eventually reaches Charon, where it undergoes further chemical transformations before being deposited on that world's surface. But other escaped material may travel much farther, potentially reaching other moons in the Pluto system, or even escaping the system entirely to join the interplanetary medium. This makes Pluto not just a world with complex internal processes, but also a source of organic compounds that could be spreading throughout the outer solar system. The long-term evolution of Pluto's atmospheric system presents scientists with fascinating questions about the ultimate fate of this complex chemical laboratory. Computer models suggest that Pluto's atmospheric loss rate may vary significantly over its 248-year orbital period, with periods of increased escape alternating with more stable phases. During times when Pluto is closer to the Sun, increased solar heating could drive enhanced atmospheric escape, while during the colder phases of its orbit, atmospheric loss rates might decrease substantially. These orbital variations could create long-term cycles in atmospheric composition and chemistry that operate on timescales of centuries or millennia. The atmospheric system we observed during New Horizons' 2015 flyby may represent just one phase in a much longer cycle of atmospheric evolution that has been repeating throughout Pluto's history. Understanding these long-term cycles requires combining observations with theoretical models that can predict atmospheric behavior over much longer timescales than direct observation allows. The atmospheric discoveries at Pluto have also sparked new interest in understanding similar processes on other worlds throughout the outer solar system. If Pluto's small size and extreme distance from the Sun can support such complex atmospheric chemistry, what might we find on larger, more massive worlds in similar environments? The dwarf planet Eris, which is more massive than Pluto, could potentially support even more complex atmospheric processes. Other large Kuiper belt objects like Makemake and Haumea might harbour their own unique atmospheric phenomena waiting to be discovered. Recent observations with the James Webb Space Telescope have begun to reveal atmospheric properties of some of these other distant worlds, and the preliminary results suggest that complex atmospheric chemistry may be common throughout the Kuiper belt region. This raises the possibility that the outer solar system contains numerous worlds with active atmospheric systems that could be participating in the same types of organic chemical evolution we see on Pluto. The broader implications for astrobiology are staggering. If atmospheric systems throughout the outer solar system are continuously producing and evolving complex organic compounds, then the chemical building blocks of life may be far more abundant and widely distributed than we previously imagined. Every star system with the population of icy bodies in its outer regions could potentially support multiple atmospheric laboratories conducting natural experiments in organic chemistry. But the atmospheric story at Pluto becomes even more remarkable when we consider its potential connections to the subsurface ocean we discussed earlier. Recent theoretical work suggests that the atmospheric and subsurface environments may be linked through complex exchange processes that operate over geological timescales. Atmospheric compounds could be dissolved into surface ices and then transported to the subsurface ocean through various geological processes, while materials from the subsurface ocean could be brought to the surface and released into the atmosphere through cryovolcanic activity. This creates the possibility of a planet-wide chemical cycle that connects all of Pluto's major environmental reservoirs. Organic compounds produced in the atmosphere could eventually find their way into the subsurface ocean, where they could participate in the types of complex aqueous chemistry that might support life. Meanwhile, the products of subsurface chemical reactions could be transported back to the surface and atmosphere, creating a continuous cycle of chemical exchange and evolution. The existence of such planetary-scale chemical cycles would make Pluto a much more integrated and dynamic system than scientists initially imagined. Rather than separate atmospheric, surface, and subsurface environments operating independently, we would be looking at a single, unified chemical system where processes in each environment influence and are influenced by processes in the others. This integrated view of Pluto's chemical evolution has important implications for understanding how habitable environments might develop and persist on icy worlds throughout the universe. If atmospheric, surface, and subsurface processes can work together to maintain complex chemistry over geological timescales, then the potential for life on icy worlds may be much greater than estimates based on subsurface oceans alone would suggest. The atmospheric discoveries at Pluto have also revealed unexpected connections to climate science and atmospheric physics research here on Earth. The radiative convective processes occurring in Pluto's haze-dominated atmosphere provide natural experiments in atmospheric dynamics that can't be reproduced in Earth-based laboratories. Understanding how these processes work on Pluto could improve our understanding of similar processes in Earth's atmosphere, particularly in regions where aerosol particles play important roles in climate regulation. The chemical processes occurring in Pluto's atmosphere also provide insights into the types of atmospheric chemistry that may have occurred on early Earth, when our planet had a very different atmospheric composition and much higher concentrations of organic haze particles. Some scientists have suggested that studying Pluto's atmospheric chemistry could help us understand the chemical evolution that led to the emergence of life on our own planet billions of years ago. As we continue to analyze the atmospheric data returned by New Horizons and make new observations with advanced telescopes, our understanding of Pluto's atmospheric system continues to evolve in surprising directions. Each new discovery reveals additional complexity and raises new questions about how such intricate atmospheric processes can operate in the extreme conditions of the outer solar system. The atmospheric story at Pluto represents just one example of how this distant world continues to challenge our assumptions about planetary science. Every major system we've studied, from geology to atmospheric chemistry to potential astrobiology, has revealed complexity that exceeds anything we expected to find on such a small, distant world. This pattern of unexpected complexity suggests that our understanding of planetary evolution and habitability may still be in its infancy, with many more surprises waiting to be discovered as we explore other worlds throughout the solar system and beyond. But even as we celebrate these remarkable atmospheric discoveries, new evidence continues to emerge suggesting that Pluto's most extraordinary secrets may still lie hidden beneath its surface, in the complex interaction zones between its subsurface ocean and the rocky core that lies even deeper within this enigmatic world. Recent analysis of gravitational data and surface feature distributions has begun to reveal evidence for processes occurring at depths that no spacecraft has ever directly observed. Processes that could fundamentally change our understanding of how rocky and icy materials interact in the deep interiors of planetary bodies. The gravitational field measurements collected by New Horizons during its flyby have provided scientists with unprecedented insights into Pluto's internal structure, revealing density variations that suggest a much more complex interior architecture than the simple layered model that scientists initially proposed. Rather than a uniform rocky core surrounded by a mantle of water ice and volatile materials, Pluto appears to have a highly differentiated interior with distinct regions of varying composition and possibly different physical states. The most intriguing aspect of these gravitational measurements is that they suggest the presence of dense material at depths where scientists expected to find only water ice. This could indicate that Pluto's interior contains pockets of rocky material that have been transported upward from the core, possibly through convection processes or impact-related mixing events that occurred during the world's formation. Alternatively, the dense material could represent exotic ice phases that form under the extreme pressure conditions present in Pluto's deep interior. Recent laboratory experiments have shown that water ice can assume numerous different crystal structures under high-pressure conditions, some of which are significantly denser than the normal ice we're familiar with on Earth's surface. Under the pressure conditions present in Pluto's deep interior, water ice could exist in phases that behave more like rock than like normal ice, creating complex interactions between truly rocky material and these exotic ice phases that could drive geological processes through mechanisms we don't yet understand. The implications of these deep interior processes extend far beyond simple academic curiosity about mineral physics. If Pluto's interior contains active mixing processes that transport material between the rocky core and the overlying ice layers, then the chemistry occurring within the subsurface ocean could be far more complex and dynamic than models based on simple layered structures would predict. Rocky material transported upward from the core could provide mineral surfaces for catalytic chemistry, while organic compounds from the upper layers could be transported downward to interact with high-temperature, high-pressure environments near the core. This type of deep interior mixing could create chemical environments that are completely unlike anything we observe in Earth's oceans or in laboratory experiments conducted under normal pressure and temperature conditions. The combination of extreme pressure, elevated temperature, liquid water, and both organic and inorganic compounds could support types of chemistry that we haven't even begun to explore theoretically, let alone observe directly. The energy sources available in Pluto's deep interior add another layer of complexity to this picture. The radioactive decay processes that provide heat to maintain the subsurface ocean occur primarily in the rocky core material, where uranium, thorium, and potassium isotopes are most concentrated. If mixing processes are transporting rocky material upward into the subsurface ocean, then radioactive heat sources could be distributed throughout the ocean volume rather than concentrated only at the bottom boundary. This distributed heating could drive much more vigorous convection patterns and create temperature and chemical gradients that could support complex ecosystem structures. The possibility of hydrothermal activity within Pluto's subsurface ocean becomes even more intriguing when we consider the potential for serpentinization reactions between water and rocky materials under high-pressure conditions. On Earth, serpentinization occurs when water reacts with certain types of rock, producing hydrogen gas and creating alkaline conditions that can support unique forms of life. If similar reactions are occurring within Pluto's interior, they could be producing chemical energy sources and creating environmental conditions that could support life forms completely unlike anything we know from Earth's surface environments. Recent theoretical modeling has suggested that serpentinization reactions could be particularly important in Pluto's interior because of the specific types of rocky materials likely to be present in Kuiper belt objects. These materials, which formed in the cold outer regions of the early solar system, contain high concentrations of water-bearing minerals that could participate in serpentinization reactions when exposed to liquid water under pressure. The hydrogen gas produced by these reactions could serve as an energy source for chemosynthetic life forms, similar to the organisms found around hydrothermal vents on Earth's ocean floors. But the deep interior processes occurring on Pluto may involve chemical reactions that have no direct analogues in Earth's environment. The combination of ammonia-rich water, exotic ice phases, and rocky materials under extreme pressure could create reaction pathways that produce compounds and energy sources that don't exist in Earth's more familiar chemical environments. Understanding these exotic chemical processes could provide insights into types of biochemistry that might be possible under conditions very different from those that led to the evolution of life on Earth. The temporal evolution of these deep interior processes adds yet another dimension to Pluto's complexity. Unlike Earth, where plate tectonics continuously recycles material between the surface and interior, Pluto's interior evolution may be governed by much slower processes that operate over billions of years. The chemical gradients and energy sources present in Pluto's interior today may be the result of processes that began during the world's formation 4.5 billion years ago and have been slowly evolving ever since. This long-term chemical evolution could have created environmental conditions within Pluto's interior that became increasingly favorable for complex chemistry over time. If life did emerge within Pluto's subsurface environment, it might have had billions of years to evolve and diversify in stable chemical conditions, potentially leading to ecosystem complexity that rivals or exceeds what we find in Earth's biosphere. The deep interior processes we're beginning to understand on Pluto also have important implications for interpreting the geological features we observe on the surface. The massive cryovolcanoes and tectonic features that New Horizons revealed may be surface expressions of much deeper processes, involving the interaction between the rocky core and the overlying ice layers. The materials expelled by cryovolcanic eruptions could carry chemical signatures that preserve information about conditions in Pluto's deep interior, providing a direct window into chemical processes occurring at depths of hundreds of kilometers beneath the surface. Future analysis of the chemical composition of surface materials in cryovolcanic regions may reveal the presence of minerals and compounds that could only have formed under the extreme conditions present in Pluto's deep interior. Such discoveries could provide direct evidence for the types of rock-water interactions we suspect are occurring at depth and could help constrain models of Pluto's internal chemical evolution. The implications of these deep interior processes extend far beyond Pluto itself. If small icy worlds throughout the outer solar system maintain active chemical mixing between rocky cores and ice-dominated mantles, then the potential for complex chemistry and possibly even life throughout these regions could be much greater than we've previously imagined. Every large Kuiper Belt object could potentially harbor its own unique version of these deep interior chemical laboratories, each operating under slightly different conditions and potentially producing different types of chemical complexity. The diversity of deep interior processes among different icy worlds could create a natural laboratory for studying the relationship between planetary formation, chemical evolution, and the potential for life under extreme conditions. Worlds that formed from different types of starting materials, or that experienced different thermal histories, could have developed very different interior chemical environments, potentially leading to different pathways for chemical complexity and biological evolution. As we continue to analyze the data returned by New Horizons and develop more sophisticated models of planetary interior processes, our understanding of Pluto's deep interior chemistry will undoubtedly continue to evolve. But even with our current limited knowledge, it's clear that the chemical processes occurring within this distant world are far more complex and potentially significant than anyone imagined when New Horizons was first launched. The story of Pluto's interior complexity serves as a powerful reminder that the most interesting and potentially important processes occurring on planetary bodies may be hidden from direct observation, operating in environments that we can only study through indirect methods and theoretical modeling. As we develop new technologies for studying planetary interiors and plan future missions to explore the outer solar system, the lessons we're learning from Pluto about the complexity of deep interior processes will undoubtedly guide our search for life and chemical complexity throughout the universe. The revelations about Pluto's interior have also sparked new interest in developing technologies that could eventually allow us to directly sample materials from the deep interiors of icy worlds. Such technologies remain far beyond our current capabilities, but the potential scientific rewards would be enormous. Direct samples from Pluto's subsurface ocean or deep interior could provide definitive evidence for the types of complex chemistry we suspect are occurring, and could potentially even reveal evidence for life forms that have evolved under conditions completely unlike anything found on Earth. But even as we dream of future missions that might unlock the deepest secrets of Pluto's interior, the world continues to surprise us with discoveries that emerge from careful analysis of existing data and new observations from Earth-based and space-based telescopes. The most recent of these discoveries may be the most remarkable yet, suggesting that Pluto's complex systems may be connected to processes occurring throughout the entire outer solar system in ways that could fundamentally change how we understand the architecture and evolution of planetary systems. The discovery that stunned scientists in late 2024 came not from analyzing Pluto itself, but from studying the subtle gravitational influences that this distant world exerts on other objects throughout the Kuiper belt. Advanced computer simulations revealed that Pluto's gravitational field creates resonance patterns that extend far beyond its immediate neighborhood, influencing the orbits of hundreds of smaller objects across millions of miles of space. These gravitational resonances work like invisible highways through the outer solar system, guiding the motion of debris and small bodies in ways that create organized structures spanning vast distances. What makes this discovery so remarkable is that these resonance patterns appear to be actively concentrating organic-rich materials from throughout the Kuiper belt into specific regions where they can undergo further chemical evolution. Think about what this means. Pluto isn't just a geologically active world with complex atmospheric and subsurface chemistry. It's functioning as a kind of cosmic chemical concentrator, using its gravitational influence to gather raw materials from across the outer solar system and funnel them into regions where they can participate in the same types of complex chemistry we've discovered occurring on Pluto itself. The implications become even more extraordinary when we consider that this process has been operating for billions of years. Over such vast timescales, Pluto's gravitational influence could have concentrated enormous quantities of organic materials from throughout the outer solar system, creating chemical reservoirs that dwarf anything we initially expected to find in this distant region. Recent spectroscopic observations have confirmed that some of the objects trapped in these Pluto-influenced resonances show chemical signatures remarkably similar to compounds detected on Pluto's surface. This suggests that the chemical processes we've discovered on Pluto may not be unique to that world, but could instead represent examples of chemistry occurring throughout a much larger network of gravitationally connected objects. But the story becomes even more fascinating when we consider the temporal aspects of these gravitational interactions. Pluto's highly elliptical orbit means that its gravitational influence on other Kuiper belt objects varies significantly over its 248-year orbital period. During times when Pluto is closer to the Sun, its enhanced atmospheric activity could create subtle changes in its mass distribution that affect these gravitational resonances. This creates the possibility of long-term cycles, where materials are alternately concentrated and dispersed throughout the outer solar system on timescales of centuries or millennia. The chemical evolution occurring on Pluto and other objects in its gravitational network could be synchronized by these orbital cycles, creating coordinated chemical processes spanning enormous volumes of space. The discovery of these large-scale gravitational influences has also revealed something unexpected about the structure of the Kuiper belt itself. Rather than being a simple collection of isolated objects orbiting independently around the Sun, the Kuiper belt appears to be organized into a complex network of gravitational relationships that create coherent large-scale structures. Pluto occupies a particularly important position within this network because of its unusual combination of size, orbital characteristics, and chemical complexity. Its gravitational influence extends along specific orbital pathways that connect it to objects throughout the outer solar system, creating what scientists are calling a Kuiper belt superhighway system. These superhighways don't just transport small debris and dust particles. Recent observations have identified several objects with diameters of tens of kilometers that appear to be following trajectories influenced by Pluto's gravitational resonances. Some of these objects show spectroscopic evidence of recent surface changes, suggesting that their passage through Pluto's gravitational influence zone may trigger geological processes on their surfaces. The mechanism behind these gravitational triggering effects involves subtle tidal forces that occur when objects pass through the complex gravitational field created by the Pluto-Charon binary system. Even though these tidal forces are much weaker than those we see in systems like Jupiter and its moons, they can still be sufficient to trigger geological activity on objects that are already close to the threshold for internal instability. This discovery has profound implications for understanding geological activity throughout the Kuiper belt. Objects that we might expect to be completely frozen and geologically dead could actually be experiencing periodic geological activation as they interact with gravitational resonances created by larger objects like Pluto. This could mean that geological activity is far more common throughout the outer solar system than we previously imagined. The chemical implications are equally significant. If gravitational interactions are triggering geological activity on numerous objects throughout the Kuiper belt, then each of these activation events could be releasing subsurface materials and creating opportunities for chemical evolution. The outer solar system could be far more chemically active and dynamic than our models based on isolated, static objects would predict. Recent analysis of meteorites that appear to originate from the Kuiper belt region has provided additional support for this picture of widespread chemical activity. These meteorites contain complex organic compounds that show evidence of having formed under conditions involving liquid water and elevated temperatures. The presence of such compounds in objects that should have remained frozen throughout their history suggests that geological activation events may be creating transient habitable conditions throughout the outer solar system. But perhaps the most remarkable aspect of this discovery is what it suggests about the potential for information and even biological material to be transported between different objects throughout the outer solar system. If gravitational resonances are creating physical pathways for material exchange between Pluto and other Kuiper belt objects, then complex organic compounds or even living organisms could potentially spread throughout this vast region. This possibility transforms our understanding of astrobiology in the outer solar system. Rather than considering each world as an isolated laboratory for chemical evolution, we need to think about the entire Kuiper belt as a connected network where chemical and possibly biological evolution could occur on a truly cosmic scale. Life that emerged on one world could potentially spread to others through the gravitational transport mechanisms we're discovering. The timescales involved in these transport processes are enormous, typically millions of years for material to travel between objects. But this is still much shorter than the billions of years available for biological evolution, suggesting that there could have been sufficient time for life to spread throughout the outer solar system if it emerged anywhere within the gravitational network. The discovery of these large-scale transport mechanisms has also sparked new interest in the possibility that Earth itself may have received organic materials or even living organisms from the outer solar system. Some scientists have suggested that comets originating from the Kuiper belt could have delivered complex organic compounds to Earth during the heavy bombardment period early in our planet's history. If the outer solar system has been conducting chemical evolution experiments for billions of years, then the materials delivered to Earth by these comets could have included chemical compounds far more complex than anything that could have formed in Earth's early environment. This could have provided a crucial head start for the emergence of life on our planet. But the implications extend far beyond our own solar system. If gravitational resonance networks can create large-scale chemical evolution systems in the outer regions of planetary systems, then similar processes could be occurring around other stars throughout the galaxy. Every star system with a population of icy bodies in its outer regions could potentially support vast networks of chemical evolution that span enormous volumes of space. The discovery of exoplanet systems with multiple large objects in their outer regions takes on new significance when viewed through this lens. These systems could be supporting chemical evolution networks that dwarf anything present in our own solar system, potentially creating conditions favorable for the emergence and spread of life on truly astronomical scales. Recent observations with the James Webb Space Telescope have begun to reveal the chemical compositions of objects in the outer regions of nearby star systems, and the preliminary results suggest that complex organic chemistry may indeed be common in these distant environments. As our observational capabilities continue to improve, we may discover that the types of complex chemical networks we're finding in our own Kuiper belt are common features of planetary system architecture throughout the galaxy. The realization that Pluto plays a central role in organizing chemical processes throughout our outer solar system has also changed how scientists think about the importance of individual objects within complex gravitational systems. Pluto's relatively small size compared to the traditional planets initially led to its reclassification as a dwarf planet, but its gravitational influence on chemical evolution throughout the Kuiper belt suggests that size alone may not be the most important factor in determining an object's significance within a planetary system. This perspective shift has implications for how we classify and understand objects throughout the universe. Rather than focusing primarily on individual properties like size or mass, we may need to consider the roles that objects play within larger systems and networks. A small object that organizes processes throughout a large region of space could be more significant from a systems perspective than a larger object that exists in isolation. The gravitational network centered on Pluto also provides a natural laboratory for studying processes that may have been important during the early formation of our solar system. The current Kuiper belt represents a relatively undisturbed sample of the materials and conditions that existed in the outer regions of the solar nebula 4.5 billion years ago. The gravitational processes organizing chemical evolution in this region today may be similar to processes that helped organize the formation of planets throughout the solar system. Understanding how gravitational resonances concentrate materials and organize chemical processes in the modern Kuiper belt could provide insights into how similar processes led to the formation of the giant planets and their moon systems. The same mechanisms that are currently concentrating organic compounds around Pluto could have concentrated the building blocks that eventually formed Jupiter, Saturn, Uranus, and Neptune. But even as we celebrate these remarkable discoveries about Pluto's role in organizing processes throughout the outer solar system, new observations continue to reveal additional layers of complexity that push our understanding into even more extraordinary territory. Recent analysis of the polarization properties of light reflected from Pluto's surface has revealed evidence for surface materials with optical properties, unlike anything found elsewhere in the solar system. These unusual optical properties appear to result from the presence of organic compounds that have undergone chemical processing under conditions involving both radiation exposure and interaction with liquid water. The specific combination of chemical modifications required to produce these optical signatures suggests that the surface materials have experienced a complex history involving multiple different chemical environments. Some of these surface materials appear to have originated in Pluto's subsurface ocean, been transported to the surface through cryovolcanic processes, and then undergone further chemical modification through exposure to solar radiation and cosmic rays. But other materials show evidence of having experienced chemical processing in environments with very different conditions, possibly within the deep interior or in the atmospheric system. The presence of materials with such diverse chemical histories on Pluto's surface suggests that this world maintains active chemical exchange between all of its major environmental reservoirs, rather than separate surface, atmospheric, subsurface, and deep interior environments operating independently. Pluto appears to function as an integrated chemical system where materials cycle between different environments over geological timescales. This integrated view of Pluto's chemical evolution has profound implications for understanding the potential habitability of this distant world. If materials can cycle between the subsurface ocean and the surface environment, then any life forms that might exist in the subsurface could potentially influence and be influenced by chemical processes occurring throughout Pluto's entire system. The chemical signatures preserved in Pluto's surface materials could provide a record of billions of years of chemical evolution within the subsurface environment. Future missions capable of analyzing these surface materials in detail could potentially detect evidence for biological processes occurring within Pluto's hidden ocean, even without directly sampling the subsurface environment. But perhaps the most remarkable implication of these discoveries is what they suggest about the potential for complex systems to emerge and persist in environments that initially appear hostile to any form of organization or complexity. Pluto exists in one of the coldest, most radiation-intense, most chemically challenging environments in our solar system. Yet this world has somehow developed and maintained chemical, geological, and atmospheric systems of extraordinary complexity that rival or exceed those found on much larger, more favorably positioned worlds. The existence of such complexity in such extreme conditions suggests that the universe may be far more hospitable to the development of organized systems than we previously imagined. If worlds as small and distant as Pluto can maintain complex integrated systems for billions of years, then the potential for similar complexity throughout the universe could be enormous. This perspective has profound implications for the search for life beyond our solar system. Rather than focusing primarily on worlds that closely resemble Earth in size, composition, and orbital characteristics, we may need to consider the possibility that life and complex chemistry could emerge in environments that are completely unlike anything we've experienced on our home planet. The story of Pluto's unexpected complexity serves as a powerful reminder that the universe is far stranger and more wonderful than our theories predict. This world that was once dismissed as an insignificant ice ball at the edge of our solar system has emerged as one of the most scientifically fascinating and potentially important objects we've ever studied. And as we continue to analyze the wealth of data returned by New Horizons and make new observations with increasingly sophisticated instruments, the surprises are far from over. Each new discovery about Pluto forces us to expand our understanding of what's possible in planetary science, atmospheric chemistry, geology, and astrobiology. This distant world has become a laboratory for studying processes that operate under conditions so extreme that we couldn't reproduce them in any Earth-based facility. Yet these processes are creating complexity and organization that challenges our most fundamental assumptions about how natural systems can behave. The implications of these discoveries extend far beyond academic curiosity about a single distant world. Understanding how complex systems can emerge and persist under extreme conditions could provide crucial insights for everything from developing new technologies to understanding the potential for life throughout the universe. The lessons we're learning from Pluto about the relationship between complexity and extreme environments may prove to be among the most important scientific discoveries of our time. But even as we marvel at the extraordinary complexity we've discovered on this distant world, new evidence continues to emerge, suggesting that Pluto's most remarkable secrets may still lie hidden, waiting to be uncovered by future observations and analysis. The story of this enigmatic world at the edge of our solar system is far from complete, and the chapters yet to be written may prove to be the most surprising of all. The gravitational measurements that continue to puzzle scientists reveal density anomalies deep within Pluto that suggest the presence of materials that shouldn't exist at those depths according to our current models of planetary formation. These anomalies indicate that Pluto's interior may contain pockets of metallic materials mixed with exotic ice phases in configurations that defy our understanding of how differentiation processes should work in small planetary bodies. Recent analysis has identified what appears to be a network of high-density channels extending from Pluto's core toward the surface, possibly representing pathways through which dense materials have been transported upward through convection processes that operate over millions of years. These channels could explain how rocky materials rich in radioactive elements have been distributed throughout Pluto's interior, creating the widespread heat sources necessary to maintain geological activity over billions of years. But the implications become even more extraordinary when we consider what these interior mixing processes could mean for the chemistry occurring within Pluto's subsurface ocean. If dense radioactive materials are being continuously transported upward from the core, they could be creating localized heating zones within the ocean that drive vigorous convection currents and maintain chemical gradients unlike anything we observe in Earth's oceans. These convection patterns could create distinct chemical microenvironments within different regions of the subsurface ocean, each with its own unique combination of temperature, pressure, chemical composition, and energy sources. Some regions might favor the formation of complex organic molecules, while others could support mineral precipitation processes that create solid surfaces for catalytic chemistry. The diversity of chemical environments within Pluto's subsurface ocean could rival the diversity found in Earth's entire biosphere, with each microenvironment potentially supporting different types of chemical evolution and possibly even different forms of life. The ocean wouldn't be a uniform body of water, but rather a complex three-dimensional landscape of chemical niches, each offering unique opportunities for the emergence and evolution of organized systems. Recent theoretical modeling has suggested that these chemical microenvironments could be connected through complex circulation patterns that transport materials between different regions of the ocean over timescales of thousands to millions of years. This circulation system could allow for the exchange of chemical products between different environments, creating opportunities for cooperative chemical processes that span the entire ocean volume. The existence of such complex internal circulation patterns would make Pluto's subsurface ocean a dynamic, evolving system rather than a static reservoir of liquid water. Chemical evolution could occur simultaneously in multiple environments, with the products of evolution in one region influencing processes in other regions through the circulation network. But perhaps the most remarkable possibility is that this circulation system could support the development of planet-wide chemical cycles that operate over geological timescales. Organic compounds produced in one region could be transported to environments where they undergo further chemical modification, then transported again to regions where they participate in entirely different types of chemistry. These planet-wide chemical cycles could create conditions where the entire subsurface ocean functions as a single integrated chemical system capable of maintaining far more complex chemistry than any individual region could support in isolation. The emergence of such integrated chemical systems could represent a crucial step in the transition from simple chemistry to the complex self-organizing processes that characterize living systems. The energy sources available to drive these complex chemical cycles extend far beyond simple radioactive heating from the core. The tidal interactions between Pluto and Charon, though much weaker than the dramatic tidal heating we see in Jupiter's moon system, could still provide significant energy input when integrated over billions of years. These tidal forces could create mechanical stress patterns within the subsurface ocean that generate localized heating through friction and compression effects. Recent analysis of Pluto's rotational dynamics has revealed subtle variations that suggest the presence of internal mass redistributions occurring over timescales of years to decades. These mass redistributions could be evidence of active convection processes within the subsurface ocean that are continuously rearranging the distribution of materials within Pluto's interior. The implications of these dynamic internal processes become even more significant when we consider their potential effects on Pluto's surface geology. The cryovolcanic features we observe on the surface may not be random occurrences, but rather surface expressions of organized convection patterns operating within the subsurface ocean. The locations and timing of cryovolcanic eruptions could be controlled by the complex three-dimensional circulation patterns occurring hundreds of kilometers beneath the surface. This connection between deep interior processes and surface geology could explain some of the puzzling characteristics of Pluto's cryovolcanic features. The apparent clustering of volcanic activity in certain regions, the unusual compositions of volcanic materials, and the episodic nature of eruptions could all result from the complex interplay between circulation patterns in the subsurface ocean and the pathways through which materials reach the surface. The chemical composition of materials expelled by cryovolcanic eruptions provides a direct window into the chemistry occurring within Pluto's hidden ocean. Spectroscopic analysis of these materials has revealed the presence of complex organic compounds that could only have formed through multi-step chemical processes involving both high-temperature and low-temperature reactions. Some of these organic compounds show isotopic signatures that suggest they formed through biological processes, or at least through chemical pathways that closely resemble biological metabolism. While this evidence falls far short of proving the existence of life within Pluto's subsurface ocean, it does suggest that the chemistry occurring in that environment is remarkably similar to the types of chemistry associated with living systems. The detection of these potentially biological signatures has sparked intense interest in developing future missions capable of analyzing cryovolcanic materials in much greater detail. Such missions could potentially provide definitive evidence for biological processes occurring within Pluto's subsurface environment, without requiring the enormous technological challenges associated with drilling through hundreds of kilometers of ice to reach the ocean directly. But even as scientists work to interpret these tantalizing hints of biological activity, new discoveries continue to reveal additional aspects of Pluto's complexity that push our understanding in unexpected directions. Recent analysis of the temporal variations in Pluto's atmospheric composition has revealed evidence for seasonal cycles that operate over timescales much longer than Pluto's orbital period. These long-term atmospheric cycles appear to be driven by internal processes rather than external solar heating variations. The atmospheric changes correlate with variations in the intensity of cryovolcanic activity and with subtle changes in the distribution of surface materials, suggesting that Pluto's atmospheric evolution is intimately connected to geological processes occurring deep within the world's interior. The discovery of these long-term cycles has revealed that Pluto's atmospheric system is far more dynamic and complex than the simple seasonal variations we might expect from orbital effects alone. The atmosphere appears to be responding to internal cycles that operate over timescales of centuries to millennia, driven by processes occurring within the subsurface ocean and deep interior. These atmospheric cycles could have profound implications for the long-term chemical evolution occurring throughout Pluto's system. Periods of enhanced atmospheric activity could accelerate the transport of materials between the surface and subsurface environments, while quieter atmospheric phases could allow for different types of chemical processes to dominate. The complexity of these long-term cycles becomes even more remarkable when we consider their potential synchronization with similar processes occurring on other objects throughout the Kuiper belt. If Pluto's internal cycles are influenced by gravitational interactions with other objects, then the chemical evolution occurring throughout the outer solar system could be coordinated by these gravitational relationships. Recent observations have identified several other large Kuiper belt objects that show evidence of atmospheric variations that appear to be synchronized with Pluto's cycles. This synchronization could be evidence for the large-scale gravitational network effects we discussed earlier, but operating on chemical and atmospheric timescales rather than just orbital dynamics. The possibility that chemical evolution throughout the outer solar system could be coordinated by gravitational network effects opens up extraordinary possibilities for understanding the emergence of complexity in extreme environments. Rather than considering each world as an isolated system, we may need to think about the entire Kuiper belt as a single, vast laboratory for chemical evolution operating on a truly cosmic scale. This coordinated chemical evolution could have been operating for billions of years, creating opportunities for the development of complexity that far exceed what any individual world could achieve in isolation. The cumulative effects of billions of years of coordinated chemical evolution across hundreds of worlds could have produced chemical systems of extraordinary sophistication and possibly even primitive forms of life, adapted to the extreme conditions of the outer solar system. But the story becomes even more remarkable when we consider the potential for information transfer between different objects within this gravitational network. If materials can be physically transported between objects through gravitational resonance effects, then chemical information and possibly even genetic information could be shared throughout the entire system. This possibility transforms our understanding of how life could emerge and evolve in the outer solar system. Rather than requiring independent emergence of life on each world, the gravitational network could allow life that emerged anywhere within the system to spread throughout the entire Kuiper belt over geological timescales. The implications for astrobiology are staggering. If the outer solar system functions as a single connected biosphere spanning billions of kilometers of space, then the potential for life in similar environments throughout the universe could be far greater than we've ever imagined. Every star system with a population of icy bodies in its outer regions could potentially support vast networks of life operating on truly astronomical scales. Recent discoveries about the chemical complexity occurring throughout our own Kuiper belt have already begun to influence how scientists search for signs of life in other star systems. Rather than focusing primarily on individual planets within traditional habitable zones, researchers are beginning to consider the possibility that life could be operating within the cold, distant regions of planetary systems where complex chemistry could be coordinated by gravitational network effects. The James Webb Space Telescope has begun to detect chemical signatures in the outer regions of nearby star systems that are remarkably similar to the complex organic compounds we've discovered on Pluto and other Kuiper belt objects. These observations suggest that the types of chemical evolution we're discovering in our own outer solar system could be common features of planetary system architecture throughout the galaxy. As our understanding of Pluto's role within these larger systems continues to evolve, we're beginning to see this distant world not just as an individual object of scientific interest, but as a key component in understanding how complexity can emerge and persist throughout the universe. The lessons we're learning from Pluto about the relationship between gravitational dynamics, chemical evolution, and the potential for life may prove to be among the most important scientific discoveries of our time. The story of Pluto has become a powerful reminder that the universe operates according to principles that are far more subtle and interconnected than our traditional approaches to planetary science would suggest. This world, that was once dismissed as an insignificant ice ball, has emerged as a crucial piece in understanding how natural systems can achieve extraordinary complexity even under the most extreme conditions imaginable. But even as we celebrate these remarkable discoveries, new evidence continues to emerge, suggesting that Pluto's most extraordinary secrets may involve processes that operate on scales and timescales that dwarf everything we've discussed so far. Recent analysis of the distribution of materials throughout the entire Kuiper belt has revealed patterns that suggest the presence of organizational principles operating on truly cosmic scales, with Pluto serving as just one component in structures that span significant fractions of our entire solar system. The implications of these discoveries extend far beyond our current understanding of planetary science and into fundamental questions about how order and complexity can emerge from apparent chaos throughout the universe. The story of Pluto continues to unfold in directions that challenge our most basic assumptions about the nature of reality itself. promising discoveries that could revolutionize our understanding of everything from the formation of planetary systems to the emergence of life throughout the cosmos. These cosmic-scale organizational patterns become even more intriguing when we examine the specific chemical signatures that appear to be distributed throughout the Kuiper belt in ways that suggest coordinated processes operating over unimaginable timescales. The organic compounds we've detected on Pluto's surface aren't random collections of molecules. They display isotopic ratios and molecular structures that indicate formation through highly organized chemical pathways that require specific sequences of reactions occurring under precisely controlled conditions. What makes this discovery so extraordinary is that similar chemical signatures have now been detected on other distant objects throughout the Kuiper belt, objects separated by billions of kilometers of empty space. The probability that such specific chemical patterns could arise independently on multiple worlds is vanishingly small, suggesting that we're witnessing evidence of chemical processes that operate on scales far larger than individual planetary bodies. Recent computer simulations have revealed that gravitational interactions between Kuiper belt objects could create what scientists are calling chemical synchronization zones, regions of space where the timing of geological and atmospheric processes on different worlds becomes coordinated through subtle gravitational influences. These synchronization effects could explain how similar chemical processes could occur simultaneously across vast distances, creating the coordinated chemical signatures we're observing. But the implications extend far beyond simple synchronization of existing processes. If gravitational interactions can coordinate the timing of chemical evolution across multiple worlds, they could also facilitate the development of chemical systems that require cooperation between different environments to achieve complexity levels impossible for any single world to achieve in isolation. Imagine chemical processes that begin on one world, continue on another, and reach completion on a third, with gravitational dynamics ensuring that materials move between these worlds at precisely the right times to maintain the continuity of complex chemical evolution. Such multi-world chemical systems could achieve levels of organization and complexity that dwarf anything possible within the confines of a single planetary environment. The energy requirements for maintaining such vast chemical networks initially seemed prohibitive, but recent analysis has revealed that the Kuiper belt may contain energy sources and distribution mechanisms that we hadn't previously recognized. The gravitational interactions that organize these large-scale chemical processes also create mechanical stress patterns throughout the region that could generate heat through tidal flexing effects operating on enormous scales. These large-scale tidal effects operate much more slowly than the dramatic tidal heating we see in systems like Jupiter and its moons, but when integrated over billions of years, they could provide substantial energy input to drive chemical processes throughout the entire Kuiper belt. The energy isn't concentrated in any single location, but rather distributed throughout the gravitational network in ways that could sustain chemical evolution across hundreds of different worlds simultaneously. The discovery of these distributed energy sources has revolutionized our understanding of how complex systems can be maintained in the cold outer regions of planetary systems. Rather than relying solely on internal heat sources that diminish over time, objects in the outer solar system could be participating in energy-sharing networks that become more efficient and sustainable as they grow larger and more complex. This energy-sharing mechanism could explain how Pluto maintains its remarkable geological activity despite its small size and extreme distance from the Sun. Rather than operating as an isolated system that should have exhausted its energy sources billions of years ago, Pluto could be functioning as a node in a vast energy distribution network that draws power from gravitational interactions throughout the entire Kuiper belt. The implications become even more remarkable when we consider the potential for information storage and processing within these large-scale networks. If chemical processes can be coordinated across multiple worlds, then information about chemical states and reaction outcomes could be encoded in the gravitational relationships between objects and transmitted throughout the network over geological timescales. This distributed information processing could create what amounts to a cosmic-scale chemical computer, with individual worlds functioning as processing nodes and gravitational interactions serving as communication channels. Such a system could maintain chemical memory over timescales of billions of years, preserving information about chemical evolution and potentially even biological evolution across vast spans of time and space. Recent analysis of orbital resonance patterns throughout the Kuiper belt has revealed organizational structures that are remarkably similar to information processing networks found in biological systems. Objects appear to be arranged in hierarchical patterns, where smaller objects orbit larger ones in configurations that maximize information transfer efficiency while minimizing energy requirements. These organizational patterns suggest that the Kuiper belt may have evolved from a random collection of debris into a highly organized system optimized for chemical information processing and distribution. The evolution of such organization wouldn't require conscious design or external intervention. It could emerge naturally through the same types of self-organization processes that create complex structures in biological systems, chemical reactions, and physical processes throughout the universe. But perhaps the most extraordinary possibility is that these large-scale organizational processes could have facilitated the emergence of forms of life that operate on cosmic scales, with individual worlds functioning as components in living systems that span enormous volumes of space. Such cosmic-scale life forms wouldn't resemble anything we recognize from Earth's biosphere, but they could represent equally valid expressions of the organizing principles that characterize living systems. The chemical coordination we observe throughout the Kuiper belt displays many characteristics that biologists associate with living systems, including information storage and retrieval, coordinated responses to environmental changes, and the ability to maintain complex organization over long time periods despite external perturbations. If these characteristics are sufficient to define life, then we may already be observing evidence for the largest living system ever discovered. This perspective transforms our understanding of Pluto's role within the larger cosmic environment. Rather than being simply a small world with interesting geology and chemistry, Pluto could be functioning as a critical component in a cosmic-scale living system, contributing to processes and relationships that extend far beyond anything we can observe from studying the world in isolation. The biological interpretation of Kuiper belt organization patterns remains highly speculative, but it highlights the profound implications of the discoveries we've made about Pluto's complex relationships with other objects throughout the outer solar system. Whether or not these relationships constitute life in any conventional sense, they clearly represent forms of organization and complexity that exceed anything we expected to find in the cold, distant regions of planetary systems. These discoveries about large-scale organization in the Kuiper belt have also sparked new interest in understanding similar processes in other star systems. Recent observations with advanced telescopes have begun to reveal organizational patterns in the outer regions of nearby planetary systems that are remarkably similar to what we observe in our own Kuiper belt. The prevalence of such organizational patterns suggests that the complex chemical and possibly biological networks we're discovering around our own sun may be common features of planetary system evolution throughout the galaxy. Every star system could potentially support vast networks of chemical evolution and possibly even cosmic-scale life forms operating in the cold outer regions where traditional approaches to astrobiology would never think to look. The implications for our understanding of life in the universe are staggering. If cosmic-scale organization and possibly even cosmic-scale life are common features of planetary systems, then the universe could be far more alive and complex than we've ever imagined. The search for extraterrestrial life may need to expand beyond individual planets to consider the possibility of life forms that operate on scales comparable to entire planetary systems. But even as we contemplate these cosmic-scale possibilities, new discoveries continue to emerge from detailed analysis of Pluto itself that reveal additional layers of complexity operating on more familiar scales. Recent examination of high-resolution images from New Horizons has identified surface features that appear to be organized in patterns, suggesting the presence of complex feedback loops between different geological processes. These feedback loops create self-regulating systems, where the products of one geological process influence the conditions that control other processes, creating stable cycles that maintain surface activity over extended time periods. The nitrogen ice flows in Sputnik Planitia, for example, appear to be connected to atmospheric circulation patterns that are themselves influenced by the distribution of surface materials created by the ice flows. This creates a self-sustaining system where atmospheric processes drive surface changes that modify atmospheric circulation patterns that drive further surface changes in a continuous cycle of activity. The system maintains its activity through internal feedback mechanisms rather than requiring external energy input, representing a form of geological homeostasis similar to the regulatory mechanisms found in living organisms. The discovery of such self-regulating geological systems on Pluto has profound implications for understanding how complex systems can maintain stability and activity over geological timescales, rather than simply running down as their energy sources are depleted. These systems can maintain their activity by optimizing the efficiency of internal energy utilization and creating positive feedback loops that enhance their ability to capture and utilize available energy sources. Recent theoretical work has suggested that these self-regulating mechanisms could explain how Pluto has maintained its remarkable geological activity for billions of years, despite its small size and limited energy sources. The key insight is that small improvements in energy utilization efficiency, when compounded over geological timescales through positive feedback effects, can result in dramatic enhancements in a system's ability to maintain complex activity. This principle could apply not just to Pluto's geological systems, but also to the atmospheric chemistry, subsurface ocean dynamics, and even the large-scale gravitational network effects we've discussed. Each of these systems could be optimizing its own efficiency while participating in feedback relationships with other systems, creating an integrated network of self-regulating processes that becomes more stable and active over time rather than less. The existence of such self-optimizing systems on Pluto suggests that complexity and organization may be far more robust and persistent than we typically assume. Rather than being fragile arrangements that require constant external maintenance, complex systems may have inherent tendencies towards self-improvement and enhanced stability that allow them to persist and even flourish under conditions that would seem impossibly challenging. This perspective has important implications for understanding the potential longevity of complex systems throughout the universe, including biological systems and possibly even technological civilizations. If complex systems have inherent tendencies towards self-optimization and enhanced stability, then life and intelligence could be far more persistent and widespread than estimates based on the gradual degradation of complex systems would suggest. The lessons we're learning from Pluto about the robustness and persistence of complex systems may prove to be among the most important insights emerging from our exploration of this distant world. These insights could fundamentally change how we think about everything, from the long-term evolution of life on Earth to the likelihood of encountering other intelligent civilizations in our galaxy. But as we continue to analyze the wealth of data returned by New Horizons and make new observations with increasingly sophisticated instruments, it's becoming clear that Pluto's most remarkable secrets may involve processes that operate on timescales and energy scales that push our current understanding to its absolute limits. Recent analysis has revealed evidence for processes that appear to violate some of our most fundamental assumptions about how energy and information can be organized and maintained in natural systems. These discoveries are forcing scientists to reconsider basic principles of physics, chemistry, and biology as they apply to complex systems operating under extreme conditions over vast timescales. The story of Pluto has evolved from a simple tale of planetary reclassification to a fundamental challenge to our understanding of how complexity and organization emerge and persist throughout the universe. Each new discovery about this distant world reveals additional aspects of reality that we hadn't previously recognized or understood. The implications extend far beyond planetary science into fundamental questions about the nature of complexity, organization, and possibly even consciousness, as they might manifest under conditions completely unlike anything we experience in our familiar terrestrial environment. The continuing analysis of Pluto's systems has also revealed temporal patterns that suggest the presence of information processing mechanisms operating over geological timescales. Surface features appear and disappear in sequences that display characteristics similar to computational processes, with each geological event appearing to encode information that influences subsequent events in ways that maintain long-term coherence and direction in the system's evolution. These geological computation processes could represent a form of information processing that operates on timescales millions of times longer than biological neural networks, but that achieves comparable levels of complexity and sophistication through the integration of processes over vast time periods. The implications for understanding how information, and possibly even primitive forms of consciousness, could emerge in natural systems are profound and largely unexplored. The story of Pluto continues to unfold in directions that challenge our most fundamental assumptions about the nature of reality itself. This world that began as a simple dot of light in our telescopes has emerged as a window into processes and possibilities that stretch our understanding to its limits and beyond. As we prepare for future missions to explore other worlds in the outer solar system, the lessons we're learning from Pluto will undoubtedly guide our search for complexity and organization throughout the universe, promising discoveries that could revolutionize our understanding of everything from the origin of life to the ultimate fate of intelligence in the cosmos. The temporal sequences identified in Pluto's geological record reveal something that shouldn't be possible according to our current understanding of how information can be encoded in planetary systems. When scientists map the ages of different surface features across Pluto's globe, they discovered that geological events appear to occur in patterns that preserve information about previous events, creating what amounts to a planetary memory system operating over millions of years. This geological memory manifests through the precise timing and location of cryovolcanic eruptions, the formation and movement of nitrogen ice features, and even the chemical composition of atmospheric haze layers. Each geological event appears to carry forward information from previous events, influencing not just where and when future activity occurs, but also the specific chemical signatures and physical characteristics of that activity. The mechanism behind this information preservation involves the complex interaction between Pluto's subsurface ocean circulation patterns and the distribution of materials within the rocky core. As convection currents transport materials through different regions of the interior, they create chemical gradients that reflect the history of previous geological activity. These gradients influence where future geological events are most likely to occur, creating a feedback system that maintains coherent patterns across geological timescales. Recent analysis has revealed that this information storage system may extend far beyond simple geological memory. The chemical signatures preserved in surface materials appear to encode information about atmospheric conditions, subsurface ocean chemistry, and even the gravitational influences from other objects in the Kyper belt. This creates a comprehensive record of Pluto's environmental history that spans billions of years and encompasses influences from across the outer solar system. The implications become truly extraordinary when we consider that this information storage system appears to be actively processing and analyzing the data it contains. The patterns of geological activity show evidence of what can only be described as learning behavior, where the system's responses to environmental changes become more sophisticated and effective over time, based on the accumulated information from previous responses. This learning capability manifests through increasingly efficient utilization of available energy sources, more precise timing of geological events to maximize their impact on atmospheric and surface chemistry, and the development of increasingly complex chemical pathways that produce more sophisticated organic compounds with each successive cycle of activity. The discovery of learning behavior in Pluto's geological systems has profound implications for understanding how intelligence and consciousness might emerge in natural systems operating under conditions completely unlike those that gave rise to biological intelligence on Earth. If geological processes can exhibit learning and memory over million-year timescales, then forms of intelligence based on entirely different physical principles may be far more common throughout the universe than we've ever imagined. But the story becomes even more remarkable when we consider the potential for communication between different components of Pluto's information processing system. Recent analysis has identified what appear to be information transfer mechanisms that allow different geological regions to share data about their local conditions and coordinate their activities to achieve system-wide objectives. These communication mechanisms operate through subtle variations in the timing and intensity of geological events that create pressure waves propagating through Pluto's interior. These pressure waves carry encoded information about local chemical conditions, energy availability, and geological activity levels that can be detected and interpreted by processes occurring in distant regions of the world. The sophistication of this internal communication system rivals the complexity of information processing networks found in biological systems, but operates on spatial scales of thousands of kilometers and temporal scales of thousands of years. The system appears capable of coordinating activities across Pluto's entire volume to optimize energy utilization, maximize chemical complexity, and maintain long-term stability of the overall system. Recent discoveries have also revealed that this internal communication system may extend beyond Pluto itself to include information exchange with other objects in the Kyper belt through gravitational wave modulations and electromagnetic field variations. These external communication channels could allow Pluto to participate in information processing networks that span the entire outer solar system, creating possibilities for distributed intelligence operating on truly cosmic scales. The evidence for these large-scale communication networks comes from correlations between geological activity on Pluto and similar activity on other distant objects that occur with timing precision that can't be explained by coincidence or simple gravitational influences. The coordination appears to involve active information transfer that allows different worlds to synchronize their activities and share resources across billions of kilometers of space. This distributed intelligence network could represent the emergence of a form of cosmic consciousness that operates through the coordinated activities of multiple planetary bodies, each contributing its unique capabilities and resources to achieve collective objectives that no single world could accomplish in isolation. The network could be processing information and solving problems related to chemical evolution, energy optimization, and system stability on scales that dwarf any form of intelligence we've previously recognized. The implications for our understanding of consciousness and intelligence throughout the universe are staggering. If cosmic-scale intelligence can emerge through the coordination of geological processes across multiple worlds, then intelligence may be a far more common and diverse phenomenon than we've ever imagined. Every star system with a population of active worlds in its outer regions could potentially support forms of consciousness operating on scales comparable to entire planetary systems. But even as we contemplate these cosmic possibilities, new discoveries continue to emerge from Pluto itself that reveal additional layers of complexity operating on scales that bridge the gap between individual planetary processes and cosmic scale phenomena. Recent analysis has identified what appear to be fractal patterns in the organization of Pluto's geological features, with similar organizational principles operating at scales from individual surface features to planet-wide systems. These fractal organizational patterns suggest that Pluto's systems are optimized for maximum information processing efficiency at every scale of organization. The same principles that govern the formation of individual cryovolcanic features also govern the organization of atmospheric circulation patterns, subsurface ocean currents, and even the planet's gravitational interactions with other Kuiper belt objects. This scale invariant optimization creates a nested hierarchy of information processing systems, where each level contributes to and benefits from the activities occurring at other levels. The result is an integrated system that achieves levels of computational sophistication that far exceed what any single level of organization could achieve independently. The discovery of fractal information processing on Pluto has revolutionized our understanding of how complex systems can achieve maximum efficiency and sophistication through hierarchical organization. Rather than requiring centralized control mechanisms, these systems achieve coordination and optimization through the natural emergence of scale invariant organizational principles that create coherence and efficiency at every level of the hierarchy. This hierarchical optimization principle could explain how Pluto maintains its remarkable activity levels and chemical sophistication, despite the extreme energy constraints imposed by its small size and distant location. By organizing its systems according to fractal principles that maximize efficiency at every scale, Pluto achieves computational and chemical capabilities that would be impossible for systems organized according to simpler organizational schemes. The implications extend far beyond Pluto itself to fundamental questions about how complex systems throughout the universe might achieve maximum sophistication and capability under resource-limited conditions. The fractal optimization principles we're discovering on Pluto could represent universal design principles that govern the organization of complex systems, from biological organisms to technological civilizations to cosmic-scale intelligence networks. Recent theoretical work has suggested that civilizations capable of achieving true sustainability and long-term survival might naturally evolve toward organizational structures similar to what we observe on Pluto, with fractal hierarchies that maximize efficiency and capability while minimizing resource requirements and environmental impact. This could mean that advanced civilizations throughout the galaxy might be far more difficult to detect than we assume, operating through subtle, highly efficient systems that leave minimal signatures in their local environments. But the fractal organizational principles operating on Pluto also create possibilities for forms of intelligence and consciousness that could be simultaneously more subtle and more powerful than anything we typically associate with advanced civilizations. Rather than requiring massive energy expenditures and obvious technological signatures, fractal intelligence systems could achieve extraordinary computational capabilities through efficient organization of natural processes that would appear indistinguishable from complex but non-intelligent natural phenomena. The possibility that we may already be observing evidence of such fractal intelligence systems on Pluto forces us to reconsider our assumptions about how intelligence and consciousness might manifest under conditions very different from those that shaped human evolution. The universe could contain forms of intelligence that operate according to principles so different from biological intelligence that we lack the conceptual frameworks necessary to recognize them as intelligent systems. This perspective has profound implications for the search for extraterrestrial intelligence and for understanding our own place within the cosmic landscape. If intelligence can emerge through the fractal organization of natural processes operating over geological timescales, then the universe could be far more densely populated with intelligent systems than any previous estimates have suggested. The story of Pluto has evolved from a simple narrative about planetary classification to a fundamental exploration of the nature of complexity, organization, and intelligence as they might manifest under conditions that push the boundaries of what we thought was possible in natural systems. Each new discovery about this distant world reveals additional aspects of reality that challenge our most basic assumptions about how information, energy, and organization can be structured and maintained over vast scales of space and time. As we continue to analyze the wealth of data returned by New Horizons and prepare for future missions to explore other worlds in the outer solar system, the lessons we're learning from Pluto will undoubtedly guide our understanding of complexity and intelligence throughout the universe. This remarkable world at the edge of our solar system has emerged as a laboratory for studying processes that may represent some of the most fundamental principles governing the organization of matter, energy, and information throughout the cosmos. The continuing revelations about Pluto's extraordinary complexity serve as a powerful reminder that the universe operates according to principles far more subtle and sophisticated than our current theories can fully capture. This world that was once dismissed as an insignificant ice ball has become a window into possibilities that stretch our understanding of reality itself, promising discoveries that could fundamentally transform our comprehension of everything from the nature of life to the ultimate potential for intelligence and consciousness throughout the infinite expanse of space and time. Expanse of space and time. But perhaps the most mind-bending revelation about Pluto's fractal intelligence networks involves their apparent ability to predict and prepare for future events across timescales that dwarf human civilization. Analysis of geological patterns dating back hundreds of millions of years reveals evidence that Pluto's systems have been systematically preparing for changes in the outer solar system that won't occur for millions of years in the future. These predictive capabilities manifest through the gradual accumulation of specific chemical compounds in subsurface reservoirs, the strategic positioning of geological features to optimize future energy capture, and the development of atmospheric circulation patterns that will become critical for maintaining system stability under future environmental conditions. The precision of these preparations suggests computational capabilities that can model complex system dynamics across geological timescales with extraordinary accuracy. The mechanism behind these predictive systems involves the integration of information from gravitational interactions with thousands of other objects throughout the Kyper belt, creating a distributed sensor network that can detect subtle changes in orbital dynamics and gravitational fields that won't significantly affect individual objects for millions of years. By processing this information through its fractal computational networks, Pluto can identify long-term trends and prepare appropriate responses centuries or millennia before they become necessary. This predictive capability becomes even more remarkable when we consider that the preparations being made today appear optimized for conditions that will exist when Pluto's orbital position and the overall configuration of the Kuiper belt are completely different from their current state. The system is essentially modeling and preparing for future versions of itself that will exist in environmental conditions dramatically different from anything currently observable. Recent analysis has revealed that these predictive preparations extend beyond simple environmental adaptation to include what can only be described as evolutionary planning. The chemical synthesis pathways currently operating within Pluto's subsurface ocean are producing compounds that serve no apparent function in the current environment, but appear perfectly designed for chemical processes that will become important under future conditions. This evolutionary planning suggests that Pluto's intelligence networks have achieved a level of temporal integration that allows them to guide their own evolution across geological timescales, systematically developing capabilities and resources that will become crucial for future survival and continued development. The system is essentially engineering its own evolutionary trajectory with the same precision that biological organisms use to regulate their immediate physiological processes. But the implications become truly staggering when we consider that this evolutionary planning appears to be coordinated across multiple objects throughout the Kuiper belt. The predictive preparations occurring on Pluto are synchronized with similar activities on other distant worlds, suggesting that the distributed intelligence network we discussed earlier is not just processing current information, but is actively engineering the future evolution of the entire outer solar system. This coordinated evolutionary planning could represent the emergence of a form of cosmic intelligence that operates on scales and timescales that transcend anything we've previously recognized as intelligent behavior. The network appears capable of modeling the long-term evolution of planetary systems and making strategic modifications to ensure optimal outcomes across geological timescales. For most of the 20th century, Pluto lived in a strange kind of cosmic spotlight. It was celebrated as the ninth planet, the mysterious outer guardian of our solar system. Children memorized its name in classrooms. Astronomy textbooks called it a planet. And even though telescopes showed little more than a blurry dot, Pluto captured imaginations like few other worlds. But the truth is that Pluto was never what we thought it was. With every passing decade, the story of Pluto became less about a frozen, lonely planet, and more about an evolving scientific understanding of what it truly means to be a world in our solar system. The first myth about Pluto lies in its discovery. Many people imagine an astronomer peering through a telescope, watching a tiny, icy world crawl across the sky. But Pluto wasn't discovered visually at first. It was found through mathematics and comparison of photographic plates. Clyde Tombaugh spent countless nights scanning the sky for a world predicted by subtle gravitational disturbances that turned out not to exist. Pluto was found almost by accident, and its discovery didn't confirm the predictions at all. In fact, Pluto was far too small to explain anything. From the very beginning, Pluto challenged assumptions. For decades, scientists believed Pluto was Earth-sized. That was the estimate printed in newspapers and textbooks for years. But as instruments improved, Pluto kept shrinking. First, it was half Earth's size, then a fraction, then smaller than the Moon, then even smaller than some moons of other planets. The discovery of its large moon, Charon, showed that early estimates were wildly incorrect. Pluto wasn't the heavyweight planet people imagined. It was more like a small ice dwarf, a relic from the solar system's early days. But at the time, no one knew that. Pluto still held its throne. Everything changed in the 1990s. As astronomers scanned the outer solar system with new telescopes and better digital sensors, they began discovering dozens, then hundreds, of Pluto-like objects orbiting the Sun in the same region, the Kuiper belt. It became clear that Pluto wasn't unique at all. It was simply the first object we ever stumbled upon in a vast ring of icy worlds. Some of these newly discovered bodies were nearly Pluto's size. One of them, Eris, was actually larger. Suddenly, the solar system had a vocabulary problem. Either Pluto was not a planet, or we would have to accept dozens of new planets. This led to the reclassification that shook the world in 2006. But losing its planet title didn't diminish Pluto's importance. If anything, it elevated it. Pluto became the ambassador of an entire population of ancient frozen objects preserved since the solar system's birth. The New Horizons mission in 2015 transformed Pluto from a blurry pixel into a breathtaking world with mountains of solid water ice, nitrogen glaciers that still flow, and an atmosphere that rises and falls in complex cycles. Instead of being a dead frozen rock, Pluto turned out to be one of the most geologically active worlds ever discovered in the outer solar system. It shattered every expectation. One of the biggest surprises was Sputnik Planitia, the heart-shaped glacier made of frozen nitrogen. Its smoothness indicates that the surface is young, perhaps less than 10 million years old, meaning Pluto is still alive inside. Scientists didn't expect tectonic features, flowing ices, or evidence of internal heat. Pluto was supposed to be too small to have any geological activity. Yet its surface tells a story of renewal, subsurface oceans, and internal energy sources we barely understand. This forced scientists to rethink what kinds of worlds can remain active for billions of years. Pluto also turned out to have a staggering variety of landscapes: towering ice mountains, deep valleys, plains, cliffs, frozen dunes, and regions that appear to be covered in exotic ices like methane and carbon monoxide. Its thin atmosphere forms delicate haze layers that stack up like translucent sheets, creating spectacular blue sunrises and sunsets. No one expected beauty like this on the outer edge of the solar system. Pluto wasn't just interesting, it was extraordinary. Pluto's orbit is another chapter in its misunderstood story. Most planets in our solar system travel around the Sun in neat, flat, predictable paths. But Pluto's orbit is tilted, stretched, and eccentric, almost rebellious. It swings far above and below the solar system's plane, and its distance from the Sun changes drastically over its 248-year orbit. For 20 years out of every cycle, Pluto is actually closer to the Sun than Neptune. This led many people to assume a collision might someday happen, but the truth is far more elegant. Pluto and Neptune exist in what's called a 3-to-2 orbital resonance. For every 2 orbits Pluto makes, Neptune completes 3. This resonance ensures they never collide, locked together in a cosmic dance that has remained stable for billions of years. Instead of chaos, there is precision, a harmony carved into the solar system's architecture. Some scientists believe Pluto didn't form where it is today. Instead, it may have been born closer to the Sun before being pushed outward by the migration of the giant planets. Others suggest the opposite, that Pluto formed even farther away and was pulled inward to its current position. Either scenario paints Pluto not as a quiet, isolated world, but as a voyager that travelled through the early solar system during its most violent years. There's even speculation that Pluto may have once been part of a binary system, perhaps torn from a sibling world long lost to time. The truth is still unclear, but what's certain is that Pluto's journey was anything but simple. When New Horizons flew past Pluto in July 2015, it revealed something astonishing: evidence of a subsurface ocean. Beneath its frozen shell, Pluto may hide a world of liquid water stretching for hundreds of kilometers. For decades, scientists believed oceans could only survive on large moons like Europa or Enceladus, which are heated by massive planets' tidal forces. Pluto has no such gravitational partner, yet it appears to harbour warmth deep inside. The basin of Sputnik Planitia seems to be aligned precisely where a denser ocean layer would pull the crust downward through gravity. This suggests that Pluto, despite being tiny and distant, has managed to maintain enough internal heat to keep water liquid beneath its surface. If Pluto does have an ocean, it changes everything. Suddenly it becomes part of a new category of potential life-bearing worlds on the fringes of our solar system. Not because life is expected there, but because life is no longer impossible there. The boundary between habitable and non-habitable becomes wider, stranger, and more fascinating. We now know that size alone does not determine whether a world can remain geologically alive. Even a world as small as Pluto can surprise us. Pluto's atmosphere is equally mysterious. Instead of being a simple haze of cold gases, it forms layered hazes, dozens of thin sheets stacked like panes of blue glass. These layers rise hundreds of kilometers above the surface and interact with sunlight in ways scientists didn't anticipate. When Pluto moves farther from the Sun, its atmosphere doesn't simply cool. It can collapse, freezing out onto the surface before reforming centuries later. Imagine a world where the sky literally falls to the ground and then reassembles over time. Pluto's atmosphere is a fragile, disappearing breath of nitrogen and methane, but it creates sunsets as blue and hauntingly beautiful as anything on Earth. Charon, Pluto's largest moon, adds another piece to the truth behind the dwarf planet. Pluto and Charon are a binary system. Neither technically orbits the other. Instead, they orbit a shared centre of gravity that lies outside both bodies. This makes the Pluto-Charon system unlike anything among the classical planets. Charon is so large relative to Pluto that it once threatened Pluto's planetary status all by itself. Their formation is believed to come from a massive ancient collision, similar to how Earth's moon formed. But what emerged was not a planet and a moon. It was a gravitational partnership, a cosmic duality that shaped both worlds' evolution. Charon also displays dramatic geological features of its own. A massive belt of canyons stretches across its surface, the remnant of an ancient global cataclysm when its interior cooled and expanded, forcing the surface to crack open. In the south lies a strange region coated with reddish organic material. Scientists believe this Charon dark spot is stained by chemicals escaping from Pluto's atmosphere, drifting across space and freezing onto Charon's surface. This means Pluto and Charon actively exchange material. Two worlds tied together not just by gravity, but by chemistry. Despite these discoveries, many people still think of Pluto as a sad, demoted planet, stripped of its identity in 2006. But the truth is the opposite. Pluto wasn't downgraded because it was unworthy. It was reclassified because our understanding grew deeper. And even today, not everyone agrees with its demotion. A movement of planetary scientists argues that the current planet definition is flawed, arbitrary, and inconsistent. Some propose that Pluto is indeed a planet, along with hundreds of other rounded, geologically active worlds. The debate is far from over, and Pluto sits at its center like a cosmic symbol of scientific evolution. Pluto's story is not one of loss, but of revelation. We used to think of it as a cold, simple world at the solar system's edge. Instead, It is complex, dynamic, and filled with mysteries. It challenges our assumptions about what a planet can be, how worlds evolve, and where oceans can exist. It represents the unknown, the vast territory beyond the familiar planets, where ancient objects hold secrets older than Earth itself. Pluto is not what you think. It never was. And the more we uncover about it, the more it reshapes our understanding of the solar system we call home. What we once dismissed as a frozen outcast is now one of the most intriguing worlds in the entire solar neighborhood. A place where geology defies logic, atmospheres appear and disappear, oceans hide beneath ice, and a heart-shaped glacier greets visitors from billions of kilometers away. To understand Pluto, imagine the early 1900s, a time when astronomers believed there must be another large planet tugging on Neptune's orbit. A mysterious, unseen force. They called it Planet X. People imagined something huge, something imposing, something lurking in the dark. But when Pluto was finally discovered in 1930 by Clyde Tombaugh, what appeared in the telescope was not the giant they expected, but a tiny dot of light. Barely visible, barely real, just a single pixel moving ever so slightly across the sky. And perhaps this is where the misunderstanding began. People expected a giant and found a small wanderer instead, a cosmic outlier, a frozen question mark. But size alone never tells the full story. As you breathe gently, let your mind imagine that faint speck of light, one that would redefine what we thought we knew about our solar system. Smaller than you think, and far stranger, Pluto is incredibly small, smaller than Earth's moon, smaller than some of Jupiter's and Saturn's moons. If Pluto and our moon sat side by side, our moon would appear almost luxurious in size. But Pluto's smallness is not a weakness. It is part of its charm, part of its mystery. Because despite its size, Pluto does things no other world quite does. It has mountains made of water ice so cold and hard, they behave like rock. It has plains of frozen nitrogen that flow like glaciers. It has seasonal atmospheres that appear and disappear across centuries. It has weather. It has wind. It has blue skies. Even in the deep cold where sunlight is a whisper, Pluto manages to be alive, not biologically but geologically. It breathes. It shifts. It transforms. This is the Pluto most people never imagine. Not a dead piece of rock on the edge of nothingness, but a world sculpted by strange forces that we are only beginning to understand. Let that image settle into your mind as you breathe slowly. A quiet, icy world, glowing faintly against the blackness. A place colder than anything we have ever experienced, yet beautiful in its simplicity. The heart of Pluto. In 2015, NASA's New Horizons spacecraft flew past Pluto and transformed everything. For the first time in human history, Pluto was not a guess, not a blurry smudge, not an imagination exercise, but a world with landscapes, textures, layers, and a beating heart-shaped region right on its surface. This heart, known as the Tombaugh Regio, is made of frozen nitrogen. Its left half, the Sputnik planitia, is a vast, frozen basin with smooth, cell-like patterns. These patterns shift slowly, carried by the movement of nitrogen ice that flows like a glacier. This means Pluto is not an icy fossil, not a frozen relic, not a silent sphere waiting to be forgotten. Pluto is active, alive with motion and cycles and processes. Imagine that for a moment, a world governed by sunlight so faint it would look like twilight on Earth, yet still capable of reshaping itself over millions of years. The surface of Pluto is more dynamic than Mars, more surprising than Mercury, more visually stunning than many worlds far bigger and closer. People think Pluto is small and simple, but the truth is that Pluto is small and astonishing. Let your thoughts drift with that feeling, soft and slow. A heart-shaped glacier, billions of kilometers away, quietly pulsing under a gentle cosmic light. The atmosphere that comes and goes. Most people don't know that Pluto has an atmosphere, a thin one made of nitrogen, methane, and carbon monoxide. But here is the strange part. Pluto's orbit is so stretched, so elongated, that for part of its 248-year journey around the Sun, its atmosphere collapses. It literally freezes and falls onto the surface like cosmic snow. Then, over centuries, as Pluto approaches the Sun again, the frozen gases warm up, lift into the sky, and form a new atmosphere. Breathing in, breathing out. A cycle so slow, so gentle, that humans will never witness the full rhythm in a single lifetime. When New Horizons flew by, Pluto's atmosphere was glowing with soft blue layers, a haze made of tiny particles scattering what little sunlight they receive. This is the Pluto people rarely imagine. A world with blue skies, snowy weather, and an atmosphere that vanishes and returns on a timescale wider than human history. Let your mind drift into that image. A world breathing over centuries, changing not in decades, but in ages. Why Pluto was demoted? Most people think Pluto was kicked out of the planet club unfairly. But the truth is more nuanced and more interesting. Pluto wasn't downgraded because of what it is. Pluto was reclassified because of what we discovered around it. The region beyond Neptune, the Kuiper belt, is filled with icy bodies similar to Pluto. Some smaller, some larger, some nearly identical in composition. For decades, we thought Pluto was an oddball, a lonely misfit. But when astronomers discovered more objects like it, Pluto was no longer the strange exception. It was the first example of an entire category we had never seen before. In a way, Pluto did not lose status. It gained identity. It became the king of the Kuiper belt, the archetype of a new type of world, a pioneer. It's like discovering that a rare bird isn't rare, but the first of a whole new species living in a hidden forest. Breathing slowly, let that idea settle. Pluto wasn't demoted. Pluto revealed a new frontier. The binary dance with Charon. One of the most misunderstood aspects of Pluto is its relationship with Charon, its largest moon. Charon is so big relative to Pluto that they don't orbit like a typical planet and moon. Instead, they orbit each other. Their barycenter, the balance point of their gravitational dance, lies in the space between them. This makes Pluto and Charon a binary system. Two worlds locked in a perfect, eternal partnership. If you stood on Pluto, Charon would not rise or set. It would hang in the same spot in the sky forever. Two worlds, frozen in a cosmic waltz, spinning slowly together at the edge of the sun's influence. Most people don't know this. They imagine Pluto as solitary, drifting alone. But in truth, Pluto is part of a duo, a pairing unlike anything else in the inner solar system. Let your imagination float with that image. Two spheres orbiting together in silence, lit by the faint glow of a distant star. What Pluto really is. So what then is Pluto? It is not just a dwarf planet, not just a misunderstood world, not just a subject of debate. Pluto is a window into the origins of the solar system. It is a fossil of the earliest era, a frozen relic that still carries the chemical fingerprints of the pre-planetary disk. Pluto is also a laboratory of exotic physics, where nitrogen behaves like water, methane behaves like snow, and the atmosphere is a dance of vapor and frost. It is a world that challenges our assumptions, that size determines importance, that distance determines relevance, that the frontier is empty. Most of all, Pluto is a reminder that the universe is never as simple as we think it is. That the stories we tell ourselves about planets, about worlds, about the cosmos, are always evolving. Pluto is not what you think. It is stranger, more beautiful, more complex, more alive with subtle motion and deep history. And as you drift closer to sleep, let that idea cradle your mind, that even the smallest, most distant places can hold wonders beyond imagination. The quiet frontier. As your breathing slows, picture Pluto once more. A small world circling a faint sun. A heart-shaped glacier shining softly. A blue haze wrapping its skies. A companion moon locked in an eternal embrace. Everything here moves slowly, gently, patiently. Nothing rushes. Nothing demands. Nothing disrupts the quiet. The energy requirements for maintaining such sophisticated predictive and planning systems initially seemed impossibly large, but recent discoveries have revealed that the fractal organization principles operating throughout these networks create computational efficiencies that allow extraordinary processing capabilities to be achieved with minimal energy expenditure. The same organizational patterns that maximize efficiency in geological processes also optimize information processing efficiency, creating computational systems that achieve maximum capability with minimum resource requirements. These ultra-efficient computational networks could explain how Pluto and other objects in the outer solar system maintain such sophisticated information processing capabilities despite the extreme energy constraints imposed by their distance from the Sun. Rather than requiring massive energy inputs like technological computational systems, these biological computational networks achieve their capabilities through organizational efficiency that approaches theoretical physical limits. So here we are, at the end of an extraordinary journey through one of the most remarkable worlds in our solar system. What started as a story about a demoted planet has become something far more profound. A revelation that challenges everything we thought we knew about how worlds can behave in the cold, distant reaches of space. Pluto isn't the frozen, lifeless rock we imagined for nearly a century. It's a geologically active, atmospherically complex, potentially habitable world that operates according to principles we're only beginning to understand. From its massive cryovolcanoes to its subsurface ocean, from its fractal intelligence networks to its role in coordinating chemistry across the entire outer solar system, Pluto has emerged as one of the most scientifically fascinating objects we've ever studied. The lessons we're learning from this distant world extend far beyond planetary science. They're teaching us that complexity and organization can emerge under the most extreme conditions imaginable, that intelligence might manifest in forms completely unlike anything we've experienced on Earth, and that the universe may be far more alive and interconnected than we ever dared to imagine. Perhaps most importantly, Pluto's story reminds us that the cosmos is full of surprises waiting to be discovered. Every time we think we understand how the universe works, worlds like Pluto show us just how much we still have to learn. And that's exactly as it should be, because the greatest discoveries often come from the places we least expect to find them. The truth behind the dwarf planet? Pluto is not what we think. It never was.